is on.
Good morning, everybody. I am Stefano Marcugini from University of Perugia, Italy, and I am your chairperson. So I am asking if the speakers are present now. We are expected to start with the first talk.
Good morning, I am Teresa Salomone and I am the first speaker.
Good morning, Teresa. Good morning. And I think that you can start with your talk. Title, I think, CFD, Prediction of Aircraft Control Surface Aerodynamics, if I am right.
Mine is CFD Prediction of Retractable Landing Gear Aerodynamics.
Okay, excuse me.
Don't worry.
Because I was not seeing your name in my list. Okay, so CFD Prediction of Retractable Landing Gear Aerodynamics, and you can start.
Okay, thank you. I will share my screen. Good morning, everyone. I am Teresa Salomone, PhD student from University of Campania, Luigi Vanvitelli. In this work, computational fluid dynamics is used to evaluate the mean aerodynamic load on a typical retractable landing gear system for a commercial transport aircraft. This was done through the use of Reynolds averaging Navier-Stokes equation with a finite volume-based numerical method. After a brief introduction, I will talk about the computational modeling, and so the methodology used to evaluate the load, the geometric model, and the particular technique used to generate the mesh. Then I will show the results and a comparison between our CFD results and experimental data. The retractable landing gear system is a crucial component in the design phase of a transport commercial aircraft. This is because it has to be as light as possible with long endurance, high performances, and while maintaining all the safety regulatory. CFD can be a tool to predict the mean aerodynamic loads acting on this type of system, but several crucial aspects need to be considered. For example, CFD must be capable to evaluate the development of the turbulent wake and its interaction with other components downstream. And also, due to the presence of moving black bodies, there could be unsteadiness that could lead to amplification in the aerodynamic load. In this case, the geometry was provided by Leonardo Aircraft Company. So, in order to design the landing gear system, it is necessary to know the aerodynamic load acting during its movement. And so, the motion law in this case is given by our industrial research partners, and it is possible to consider a linear approximation for a general loading coefficient CF that depends on the partial derivatives, both with respect to the angle of attack and the side slip angle, and from a coefficient CF0 that depends on the configuration for which both the angles are zero. One of the goals achieved with this work was the use of a geometric model that is really similar to the real geometry. And here we can see the movement of the landing gear strut from stalled position to deployed position. This deployment takes place in 10 seconds. Here also we can see a side view of the aircraft with the angle of attack, and a plan view with the side slip angle that is positive from the left to the right with respect to the pilot view. The dynamic mesh technique used in this case is a technique that allows the mesh to move together with the movement of the landing gear strut. In order to avoid the degradation of the mesh, two techniques are used. One is the smoothing that allows to move the mesh without changing the number and the connectivity of the cells, and the remeshing technique that allows to add or delete cells where the boundary displacement is too high with respect to the local mesh size. It is not necessary to have a dynamic mesh active in the whole domain, but only in the region where the rotation actually takes place, so near the bay, the wheels, the landing gear strut, and the doors. Here we can see a figure of the whole domain mesh with a close-up view of the gear cavity. Also, we can see how the mesh moves together with the landing gear strut. Three cases are presented, one with zero angle of attack and zero side slip angle, one increasing the angle of attack to 4 degrees, and one with a side slip angle of 5.7 degrees. The last case need a mesh of 5 million cells, while the two previous cases, due to symmetry of the flow, only need 1/2 of the domain. Here we can see an example of pressure distribution coefficients during the deployment phase for the first case, and also the skin friction coefficient distribution. These contours are preliminary to the evaluation of the coefficients acting on the landing gear strut, the force coefficients. Here also we can see the velocity contour in the first case and in the third case. We can see how in the first configuration with zero side slip angle, there is the need of only 1/2 of the domain. And so we can see the time history of drag lift coefficients acting on the gear structure. Both coefficients from stalled position start from very low values, then the drag coefficient starts to increase during the deployment phase, reaching its maximum at about 6 seconds. we can see the strong effect of the side slip angle both on downwind and upwind door that leads to an increase in drag coefficient. Both coefficients, when the deployment is complete, remain in a steady state position. The effect of the side slip angle can be seen also on drag lift coefficients acting on the doors. And on drag coefficient, we can also see the difference between what happens on the downwind door and the upwind door. This is due to asymmetry of the flow and the development of a strong turbulent wake, especially in the third case. And also we can see on lift coefficient that when the deployment is complete, there is an increase in lift coefficient. This is because the surface door acts as an additional lift surface. Then from hinge moment coefficient, we can see that again it starts from low values when the landing gear is stowed, and it starts to increase. In this case, the hinge moment is assumed positive in the direction of the door's opening. And also there is the difference between the downwind door and the upwind door. And we can see this increase on the downwind door in the hinge moment coefficient, justifying also the behavior seen before or lift coefficient. Here we can also see the effect of the angle of attack. The hinge moment coefficient increases together with the angle of attack. Then we have a comparison between experimental data and CFD results in terms of maximum and minimum normal force. We have a good agreement, an absolute error of about 0.1. The only discrepancy is at low opening angle on the maximum normal force achieved. This can be due to the fact that the present simulation does not reproduce all the experimental configurations that was investigated, and also in this case we are using a geometric model that is not identical to the real geometry. So to summarize, the present study can be intended as a preliminary design tool in order to evaluate the aerodynamic load acting on this typical retractable landing gear system for a regional transport commercial aircraft. This was done using a simplified models derived from a real geometry and using a dynamic mesh technique. We have shown the results in terms of drag coefficient, lift coefficient, and hinge moment coefficient, and we have an acceptable agreement with empirical data and our CFD results in terms of normal forces achieved. I would thank Leonardo Aircraft Company for providing the landing gear data, and I would thank you all for listening.
Okay, thank you very much. And are there any questions or comments? Okay, if there are no questions, I think we can pass to the second talk.
Okay, thank you.
Thank you again. And the second talk is connected, I think, with the previous one, and the title is CFD Prediction of Aircraft Control Structure Aerodynamics. I think Nunzio Natale is speaking.
Good morning.
Good morning.
I'm going to share my screen.
Okay. I think you can start.
Okay. Sorry. Can you see my screen?
Yes, we can see.
Okay, thank you. Good morning. I'm going to present our work CFD prediction of aircraft control surfaces aerodynamics. This is just a brief outline of this presentation with a brief introduction, computational model used, results, and conclusion. The present work is focused on the integration of CFD in the preliminary design development of original transport aircraft, and in particular focused on the control surfaces aerodynamics. About the control surfaces, every control surface has been considered one at a time. So once, for instance, the aileron has been deflected, all the others are considered undeflected. Upper and lower gaps of the control surface have been closed, considering the Mach number, the flight Mach number, or the Mach number used for the calculation is anyway below 0.5. Results have been verified either with semi-empirical or vortex lattice method. And loading distribution evaluated by CFD have been compared to the undeflected or clean configuration. This is basically the geometry of the clean configuration where no deflection has been imposed. Here, the configuration for the deflected aileron for technically the deflection of the aileron with some details. Here, the configuration with the deflected elevator plus minus 10 degrees. 10 degrees on the left and minus 10 degrees on the right. Here, some details about the computational mesh that has been used for the clean configuration first. Then some details about the configuration with deflected ailerons. Sorry. And here, the configuration, some details for the tail of the configuration with deflected elevator. So the flow condition considered for the calculation, Mach number 0.2, Reynolds number about 12 millions. The computational approach used, relatively simple, is due to the fact that the database developed has been used in a pre-design phase where not all the design aspects have been frozen yet. So there is a balance between accuracy and computational time required. The loading distribution calculated by CFD has been verified using first the VLM code AVL. A simplified wing geometry has been used for this purpose for both code, where some features like nacelle and winglet have been removed from the original model. To properly compare the two codes, in CFD we performed an in-visual calculation with the in-visual model available in the code, and the comparison has been performed at the same lift coefficient. There is a good agreement between the two code in terms of span-wise loading. And here some result about the clean configuration in terms of drag polar and pitching moment coefficient. This result will be used to compare the results obtained for the configuration when the control surface have been deflected. Here, just a breakdown of the pitching moment coefficient with the various contributions. The red line corresponds to the full model. The green line, green curve to the wing body, and the gray one to the body plus vertical and horizontal tail. Here, the loading distribution for the configuration with the defective ailerons is presented compared to the clean configuration. One thing to be noted here is that the loading have been calculated just before the winglet. So the winglet, the part of the wing that part of the wing basically is not considered in this graph. So the winglet are not included. And here, the result in terms of roll moment, compared to the WM code. One can see a certain loss in effectiveness of the control surfaces that has been highlighted by the CFD, and of course is not seen by the WM code that is basically envisaged. Here are some results for the elevator deflected configuration. In terms of drag polar and pitching moment coefficient. The results in terms of delta pitching moment are in agreement with the results provided by our industrial partner. These results, I'm afraid, that cannot be shown due to industrial secrecy, but we found a good agreement between our results and the one provided by them. Here, the loading distribution on the horizontal tail for all the configuration analyzed. In particular, one can see how the maximum loading does not correspond to the initial section, and it slightly moved towards the tip. This is in agreement with the industrial data provided as well. And just to conclude this presentation, the possibility to use CFD in an advanced pre-design phase with a simplified CFD approach has been proved. And the result in terms of coefficient and aerodynamic loading is in agreement with the data provided by our industrial partner. Of course, there remains possibility to use more sophisticated computational model and to improve the present computational approach. For instance, considering in the loading calculation the presence of the winglet, and that will be possibly the next step for this work. And of course, the model can be improved depending on the accuracy required in the particular design phase and computational resources. Authors would like to thank Leonardo company for providing the provided geometry, and thank you for listening.
Okay, thank you very much. Are there any questions or comments? Okay, if there are no questions, I think we can start with the third talk. I think we see the third speaker. So,
Hello.
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 Welcome.
Thank you.
And the title of the third talk is Optimal Online Electric Vehicle Charging Scheduling in Unbalanced Three-Phase Power System. And who is speaking, please?
I'm Iman Zaidi. But it's like I can't share my screen. Excuse me for 1 minute.
Yeah.
It's like the browser didn't allow me to share my screen.
Yeah. Raffaele, can you help? Maybe.
It's Firefox.
You should, in the bottom left, you have a share icon. Okay, share your screen.
Excuse me?
If you go in the bottom left of your screen, you have
Yeah, I clicked. It's like the Firefox browser can.
We have
Yes.
no problem with Firefox yesterday. So you have a PDF of your presentation or PowerPoint.
Yeah, I have a PDF of my.
Then try to share not the Firefox window, but the desktop, the first tab on the left.
The first tab on the left.
Okay.
Yes, ma'am.
On your first share icon, you should have a 3-tab window. In the first tab, you call share your desktop.
This one is shared.
Yeah. But it doesn't show.
Vous pouvez juste avoir votre écran, écran entier.
No.
Okay. Another way is if you have Chrome, try to use Chrome instead of
Tu peux utiliser Chrome, t'as Chrome ou t'as pas Chrome?
J'ai pas Chrome, c'est pour ça.
Chrome, t'as mis dans Chrome.
Non, c'est dans le. It's the browser. Firefox doesn't allow me to share.
Okay. Do you have another browser like Chrome?
No, Edge.
Internet Explorer.
No, also
Doesn't work.
doesn't work also. So I need Chrome and I don't have.
Chrome ou Firefox. Ok, Firefox.
Okay. The flash disk.
Okay. Professor Marcugini?
Yes, I'm here.
Maybe we can go on with the next presentation until Professor Zaidi come back, because I think she lose the connection.
Okay.
Thank you.
Okay. Indeed, the next speaker is me, and my so.
Live streaming is on.
Hello.
Hello.
Just 1 second. I will use another laptop.
Okay, so you can try to start your presentation.
Yeah, thank you. Ouais.
voglio dire. Scusi.
Je vous envoie le lien.
Tu je sais pas. Tu nous envoies par Slack.
Oui, pardon.
C'est facile par Slack.
Ouais, je l'ai pas.
Maybe we can go on with the next presentation while we try to fix the problem.
Yes, I think also because now is the scheduled time for the fourth presentation. So I think I give my presentation, then we can go back to the missing one. So.
La musica. Okay.
My presentation is about coding theory, and its title is Bounds for Complete Arcs in PG3Q, and covering cause of radius 3, codimension 4, under certain probabilistic conjecture. I start giving basic mathematical definitions, then I show upper bounds obtained by computer, and then the general theoretical bound up to a probabilistic conjecture, and then I give a sketch of the proof. In the vector space of dimension n constructed over the finite Galois field of order q, a linear code is a subspace. We denote its dimension by n minus r and call small r the redundancy of the code. D is the minimum distance. That is the smallest number of coordinates where two code words differ, and it is related to the error correcting capability of the code. The greater the minimum distance, the better. The covering radius, big R, is the least integer such that the space fq power n is covered by the spheres of radius r centered at the code words. Covering cause apply to data compression, decoded errors and erasures, football pools, and write-once memories. Good covering codes have small density. That is the ratio between the total volume of the covering spheres and the volume of all the space. Fixed Q, redundancy, and covering radius, covering density decreases with decreasing n. So we are interested in covering cause with small density. We would like to have covering cause with small length. So we denote the smallest length of a covering code given a certain redundancy, a certain covering radius, and maybe a certain minimum distance with this LQ notation. There are lower bounds about the smallest length of covering code for Q large enough of order the redundancy minus the covering radius over the covering radius. And it holds under certain conditions on Q. We would like to obtain also upper bounds. In this paper, we consider covering codes of covering cause of redundancy 4, covering radius 3, and minimum distance 5. They are MDS cause. That means that the minimum distance is the greater possible given that length and dimension. And they are quasi-perfect. That means that the covering spheres of radius R overlap, but the spheres of radius R-1 do not overlap. Note also that there exists just a few perfect covering codes, where the covering spheres of radius R do not overlap. To find our bounds, we exploited a correspondence between covering codes and certain geometrical objects, the complete arcs of the projective space PG and Q. The correspondence is obtained considering the points of the complete arc in homogeneous coordinates as the columns of the parity check matrix of the code. For our code with these parameters, the correspondence is with the complete n arc of PG3Q. What is precisely an n arc in PG3Q? It is a set of endpoints such that there are no 4 points belonging to the same plane. It is complete if it is not contained in an n+1 arc. An example of complete arc in PG3Q is the twisted cubic curve of this equation, and it has Q+1 points. And in this case, this is the greatest possible size for an arc. But we are interested in complete arcs of small size to have covering codes of small density. The lower bound seen before is of order cubic root of Q. We found an upper bound that has an additional factor cubic root of log Q. For relatively small values of Q, we worked by computer using a greedy algorithm until Q about 43 hundredths, and then an algorithm that at each step adds a point to the partial solution without search, selecting the first non-covered points from a fixed list until Q about 7,000. You know what a greedy algorithm is. In this picture, we see the results of a computer search. Of course, the greedy algorithm behaves better, but not so better. In both the cases, the order of the smallest length of the complete arcs and therefore of the corresponding covering codes is of order cubic root of Q log Q. For Q big enough, we obtain theoretical bounds based on a probabilistic conjecture. The order is again cubic root of Q log Q with a constant less than 3. We obtained this bound studying the behavior of a hypothetical greedy algorithm which at each step has one new point to the arc. The added point provides the maximum possible number of new cover points. So that be delta W, the number of new cover points at the W1 plus 1 step of the algorithm. We computed a lower bound on the number of candidates to be new cover points in the W plus 1 step, and this bound has been obtained considering the geometrical properties of PG3Q. We denote this bound by omega W. We also found, using the symmetry properties of PG3Q, that the uncovered points are uniformly distributed in PG3Q, and the probability to be uncovered is independent of a point. This simulated in formulating this conjecture that states that for Q large enough, the number of cover points at each step is not smaller than the expected value for the case when for points the events to be uncovered are independent. Now that this conjecture gives a lower bound on the number of new cover points at each step of the algorithm, we can ask how many steps W are needed to obtain a complete arc. For Q big enough, we can write inequalities on the number of uncovered points at each step, obtaining lemma 2. For intermediate values of Q, we wrote a recurrence relation based on the bound conjecture on the number of covered points and solve it by computer, obtaining lemma 3. This last picture summarizes the results. We see in black the computer results, in blue the first kind of theoretical results based on the study of the recurrence relation, and for Q big enough, the general bound obtained studying some inequalities. Okay, it's all. Thank you for your attention. Are there any questions or comments? Okay, if there are no questions, I think we can retry with the third talk about the optimal line electric vehicle charging scheduling.
Yeah, thank you. So I'm sorry for the problem.
Okay. I can see the slides.
Yes.
Okay, you can start.
Yes. So okay, thank you. Hello everyone. My name is Iman Zaidi. I'm a PhD student at Erimas Lab in University of Upper Alsace in France. Today I will be presenting our work on optimal online electric vehicle charging scheduling in unbalanced three-phase power system. Here's an outline of the presentation. We will start with the introduction, then problem description, online optimization algorithm, and simulation results, and the end in a conclusion. So, electric vehicle has recently gained worldwide interest as a promising technology to reduce carbon dioxide emissions. However, recent studies shows that charging a large number of electric vehicles at the same time can easily overload the power grid and leads to other undesirable impacts such as power losses and voltage deviations. To address the problem, so a promising direction is to optimally schedule the electric vehicle charging. This means control the charging load while being aware of technical and economic constraints of the power grid. We move now to the problem description. Here's the scheme showing the design of the considered charging station. As we can see, this charging station is fed with a three-phase current power source. Thus, there is three lines as pointed, line 1, 2, 3, and each line regroups a number of power outlets where an electric vehicle can be plugged in for charging. Each electric vehicle has its own parking space, and it has its arrival time, departure time, and charging time. However, in real life settings, the electric vehicle driver can plug his vehicle into the outlet at any time. So these informations are prior unknown to the charging station before the actual arrival of the electric vehicle. Moreover, considering the characteristic of three-phase power system, we have two more constraints to consider. A max load constraint, so we can charge only an electric vehicle at the same time in each line, and the load balance constraint, which means that the difference between the number of electric vehicle being charging at the same time in any two lines cannot exceed certain amount delta n. So here is an example of charging operation of an electric vehicle I. Suppose that the electric vehicle arrive at a arrival time Ry and the departure time dy, and it has to charge for 5 time slots, but we cannot start charging the electric vehicle at this time slot due to max load or imbalance constraint. So the charging will begin as at this time slot, and it will complete at this time slot. So it will result on a tiredness, and the objective of the schedule is to minimize this tiredness for each electric vehicle. So now we present the proposed algorithms to solve the previous optimization problem. Since the problem is then dynamic and real-time, it requires online electric vehicle charging scheduling algorithms. At first, we consider the non-preemptive scheduling, where the charging of an electric vehicle cannot be interrupted until it completes charging. For this case, we propose an heuristic based on PRTT dispatching rule. And on the other hand, we investigate the case study where preemption is allowed. Thus, the charging of an electric vehicle can be interrupted and resumed afterward. For this case, we propose a heuristic based on PRTT rule also, and a local search to improve the total tiredness. For the non-preemptive scheduling algorithm, we proposed a PRTT-based algorithm. For each time interval, for each line, we calculate the PRTT value of each announced scheduled charging operations as the maximum between the departure time and the T plus the charging time of each vehicle. And these charging operations are ordered in increasing order of their PRTT rule, PRTT value, and then we add the first one to the schedule without breaking imbalance and max load constraint. In the end, if the assignment of a charging operation breaks the previous imbalance constraint, we redo the affectation for this time interval. For second algorithm, it concerns preemptive scheduling. It's the same as the previous algorithm, except for here we change the value of considering all the charging time, but only the remaining charging time of each charging operation, and we schedule only at this time. So no scheduling is affected for the next time slots. For the third algorithm is a local search. We propose a local search to explore solution with better tiredness. Here's an example for a solution representation. We have here the interval and here the 3 lines. And in each case, it's the number of the index of the electric vehicle being charging at this time interval in this line. So at each time interval, a partial schedule is built using the PRTT-based heuristic. Then a hint clipping strategy is used to improve the partial schedule. We generate the neighborhood of a solution considering only the next time slot and replace the actual solution with the best solution so found. As any local search, neighborhood solution need to be generated. So we consider for movement to build the partial to generate the neighborhood solution: a shift right and a shift left, a shift right on the 3 lines and a shift left on the 3 lines. So here an example of shifting left. Consider that we are here at this time slot, so we can only buy the schedule for the next time slots. We take an electric vehicle and we move it to another time slot to be charged if it doesn't break the constraint of imbalance and max load constraint. So for simulation result, we consider the benchmark proposed in the reference below. There are a total of 180 outlets, and the arrival charging departure times are generated following a normal distributions. And there are three scenarios. The first scenario is a normal weekday. The second scenario, where is the most of electric vehicle arrive at the same time, so it makes it harder than scenario one. And this the third scenario is the second scenario with the tighter due date. So scenario 2 will be harder to solve than scenario 1. And for each scenario, there is two types of instances were generated, where the distribution of electric vehicle on the three lines are different. For type 1 instances, 1/3 of electric vehicle arrive at each line. For the second type, we have 16% of vehicle arrives to line 1, and 30 for line 2, and 10% to line 3. This makes the imbalance constraints hard to solve. For each type, in each scenario, we generate 30 instances were generated, and for the value of n, it's the max number of vehicles that can be charging at the same time in one line. We have 3 value for n, and for delta we have 4 the value of delta. So the tardiness is calculated for each instance and then summed up for each group, and the results are compared with the proposed algorithm of non-preemptive online heuristic in the reference below. So as we can see in the PRT, we calculate the percentage of increase or decrease in total tightness compared to the proposed heuristic. A positive number, it means that there is an increase in total tightness, and a negative number, negative percentage, it means that there is a decrease in total tightness, which means that our proposed solution is better when there is a negative percentage. So as we can see for the PRTT, there is an increase in type 1 instances, but for type 3 instances, there is a decrease in the total tightness, which means that the PRTT heuristic is more preferred when in the hardest scenario to solve, since the type 2 are the hardest scenario than the type 1. For preemption, for the two preemptive algorithm, it outperforms the previous proposed heuristic, since allowing preemption is not redundant and makes the problem easier to solve. And as we can see, there is a really significant decrease in total tardiness for type 1 instances, and less in type 2 instances. It's much harder to solve. So as a conclusion, we proposed heuristic and the local search procedure to solve the online charging scheduling problem while maintaining the 3-phase system constraints. Simulation results show that our heuristics outperform other heuristics for most instances. And we showed also the effectiveness of preemptive scheduling in reducing the total tardiness through the experimental results. Further future work may involve more realistic objective as economic objective, or minimize the charging electricity bills paid by the charging station. Thank you for your attention.
Okay, thank you very much. Are there any questions or comments? Okay, if there are no questions, I think we can close here this section. I thank all the speakers and all the participants, and happy continuing with participating into this conference. Greetings to everybody.
Good morning, everyone. Welcome to our session. Good morning.
Hi,
So,
good morning.
Morning.
in our session today, there will be 4 presentations. And the first talk, the first paper is about numerical simulation of the reactive transport at the pore scale. And the authors are Vadim Lisiska and Tatiana Nachkova. Sorry for my poor pronunciation. And who is going to present this
It's
study?
gonna be me, Vadim.
Okay, so Mr. Vadim Letiska is going to present the numerical solution of the reactive transport at pore scale.
Okay. Okay, can you see my screen?
Yes, we can see.
Yes.
Great. So the title was already announced, and well, first of all, good morning, everybody. At least those of you who are still in the morning time zone. So my talk is about numerical simulation of reactive transport at the pore scale, and I'll start with the motivation and then why we will need all this stuff. And the idea here that if we are talking about enhanced oil recovery, about CO2 sequestration or geothermal fields exploration, we always should think of the reactive transport, because what we inject into the reservoir is typically kind of aggressive reactive gases fluid saturated with mainly saturated with CO2, which gives us quite an aggressive acid inside the reservoir, whereas the reservoirs are typically at least those we are thinking about, they are carbonates, and of course we expect the dissolution of the matrix and changes of the transport properties of the reservoir and mechanical properties and probably leakage of the cap rock and leakage of all the gases into cap rock, which we need to prevent. And that's why we're focused on the reactive transport in application to geosciences. So, and the thing here is that if we're talking about reactive transport in application to geosciences, people typically think about the macro scale model, the transport at the reservoir scale, where we need to know such parameters like permeability or diffusion and stuff like this. Or if we are talking about macroscopic models for the elastic properties of the reservoir, we also faced with permeability and bioparameters and stuff like this. But all these relations, all these parameters, they came from. Sometimes we're happy to have them from lab, but mainly they're empirical. And we need to know how they evolve, how the actual permeability of the rock changes when the rock dissolves, and then put these parameters into macro scale models. And that's why we're focused on the pore scale simulations. So what we are doing here, that we're solving the statement of the problem is quite standard. We're solving the stock equation to know the flow rate, and then we simulate the reactant transport using advection diffusion equation, and we also need to take into account the boundary movement, which is the main topic of the research actually. And to account for the boundary movement, we were using level set method, which is quite well known in computational fluid dynamics, but not that widespread in reactive transport. But nevertheless, so to follow the changes of the interfaces, to follow the changes of the pore spaces, we're using a level set method. The idea is that we introduce, instead of just having a binary image, of our rock sample, we are using the artificial function, which can be seen at which is the distance, which represents the distance from the interface to the current point in the model, and it can be viewed like a topography of your map, like hills and stuff like this. So and this level set evolves during the simulation, of course, and its evolution is dictated by the reaction rate and the amount of the reactant near the interface. And then we also combine it with the immersed boundary method using sharp interface method. And so I just show few pictures like this. So if we don't know the values of your function in yellow circles, we need to extrapolate them through the interface. So the filled circles represent the field inside the pore space, and the transparent ones are in the matrix. And we don't know field in the matrix. There is no flow field or concentration field in the matrix, so we need to extrapolate them through the boundary and then do some mathematical tricks to do it. And then we finish up with the numerical code, which is implemented using GPUs to simulate reactive transport at the pore scale. And here are 4 different examples of what is going on at the pore scale if we try to inject the try to inject chemically active fluid. And these 4 pictures here in the middle, they correspond to completely different scenarios. So what is the goal of our research is to understand how can we, if we change the macroscopic parameters like flow rate, like reaction rate, and diffusion, molecular diffusion in our fluid, how it would affect the pore space, the changes of the pore space in the rock, and the changes of the macroscopic parameters, transport parameters of the rock, like porosity, permeability, and tortuosity. And so what we did, we considered more statistically generated models of the pore space, and then simulated reactive transport varying the input parameters, and see completely different scenarios, like the one in cluster 1 and cluster 4. Or here we can clearly see the formation of the wormholes, which significantly increases transport properties of the rock, but not with almost no effect on the elastic properties, because the strength of the sample doesn't change at all, and we cannot see it from time-lapse seismics, for instance. So, and of course, we need somehow we are mathematicians, and we need to characterize these changes somehow. And we decided to take a look at the topological characterization of the pore space, and using Betti numbers, which represent like isolated pores, isolated connected bodies, or the channels, or voids inside. And we can not only compute these Betti numbers for the static for a single sample. We can compute them during the simulation, and then construct what is called persistent diagram, which allows us to see how many connected bodies we have in our pore space, and how they evolve when they appear and then they disappear. So they can appear, well, they can appear if some pores became closed, or they can disappear if two different pores connect due to the dissolution of the pores of the matrix. And these diagrams, for instance, this blue one and the red one, okay, both of them are on the same plot, they are completely different for different scenarios. You can see that the for the red one, where we've got the extremely high dissolution rate, all of the disconnected bodies got connected quite fast, and we don't have them staying disconnected for a long time, and the red dots are pretty much on the diagonal. And these diagrams can be used. We can now, if we have these diagrams, we can introduce the metrics in there and use these metrics to classify the changes in the pore space. So, and what we did, we varied the flow rate, the blue circles over here. We varied the diffusion coefficient and the reaction rate, and see what happened there. We did a lot of simulations. It was like 400 something simulations for the same statistically generated models, statistically the same models, and varying the other three parameters which I told about. And then we constructed the persistent diagrams and applied the clustering with respect to the metrics in the persistent diagram space, and that's what we see. So we see that the 4 different clusters were formed, and they are formed accordingly. So we use metrics in the persistent diagram space. We use metrics in which allows us to separate the changes in the pore space, and then took a look at what is it connected with the input parameters of the model, and we see that yes, indeed, different input parameters, different reaction rates, for instance, gives us completely different dissolution scenarios. Yeah, and here I've got some illustrations on that. Sometimes we've got quite nice wormholes. Sometimes we've got quite nice fronts, like in cluster 3. It's just dissolved as kind of forming a front with nothing left after the reactant, and quite a poor penetration of the reactant in advance. And well, for cluster 2, we've got reactant being pretty much everywhere and slowly reacting with the matrix. And of course, we try to see is it possible to connect these clusters with what is going on at the macro level, and if we can use these clusters to somehow classify what would happen with porosity, tortuosity, and permeability. And you see these plots over here that again we just consider the changes in the pore space, and then related to the tortuosity and porosity changes, and they quite nicely describe the relation between porosity and tortuosity. And that's pretty much it. So what was it all about? Is that we were trying to do a numerical simulation of the reactive transport in the pore space to quantify the changes in the pore space and quantify and relate it to the changes in the transport and mechanical properties of the rocks at the macro scale. That's pretty much it. Thank you for attention.
Thank you, Professor Vadim. Would you like to ask any questions to Professor Vadim about his work? If no questions, I would like to ask one. Professor, you mentioned different scenarios, and you showed 4 different figures to us, and each figure was presented at t equals to 300. Did you find out that t equals to 300 was the steady state case, or why did you in particular present your results at that time level?
It was just chosen. So at this particular time, we can already see the real changes happening in the rock. The further we go, the stronger dissolution will be, or the reaction would never go at all if we have low, downholder numbers and stuff like this. So it's just for illustration, because of course, if we go further, the wormholes are gonna get longer and well, yeah, there is no particular reason. Yeah, it's just.
Okay, thank you very much. That's a really interesting topic. Thank you for your presentation again.
Thank you.
Now let's continue with the next presentation. There are 4 authors of this study: Diana Conte, Maria Pia Dorenzio, Rafael D'Ambrosio, and Beatrice Paternoster. Again, sorry for my poor pronunciation of the names. And who is going to present the presentation?
Me, Maria Pia D'Arienzo.
Maria Pia. So Professor Maria Pia is going to present multi-value almost collocation methods with diagonal coefficient matrix.
Yes.
I would like to remind all of the speakers that we are given 10 minutes for the presentations. Thank you.
Okay, can you see my screen?
Yes, we do.
Okay,
thank you.
Good morning, everybody. I'm here today to present this work written together with Diana Conte, Raffaele D'Ambrosio, and Beatrice Paternoster. We focus our attention on the development of methods for the solution of stiff problems of ODs, which comes from, for example, the space discretization of time-dependent PDEs, or from a lot of mathematical models, and also from multiscale models. For example, we can consider an example in immunology, in which we have 2 different time scales, one in an extracellular level and the other one in intracellular one. For the solution of this type of problems, of course, there are other methods, such as the classical one, like Runge-Gutta methods, but they suffer from order reduction. So if we have a method with m stages, in order to be stable, the effective order is p equal to m. If we use 2-step methods, we can increase the order of 1, while with the multi-value methods, we can have that the order is equal to m. We propose these methods, which on a uniform grid take this form. We have 2 equations. The first one is for the internal stages, while the second one is for the external ones. As we see, this method depends on 4 matrices: the matrix A, B, U, and V. And we use the Nordic form for the approximation of the external stages. We want to extend this method smoothly, and we do that using collocation. So we impose that the solution is approximated by a polynomial which depends on these functions alpha and beta, which are polynomials too. And we have to impose interpolation conditions and collocation conditions too. So in order to define the method, we need to find these functions alpha and beta, because the metrics of the methods are characterized by their values in some points, which are the collocation points, and by the derivatives of this function in 1. there are some theorems about the order condition of these methods. For example, we have these order conditions which are obtained by the discretization of by the tailoring expansion of the truncation error. And we know that in order to be a stable the method, the following constraint should be fulfilled. So the number of external stages is less or equal to the number of internal stages plus 1. And we have this corollary which shows that the maximum order achievable is 2m. Also, we can write an equivalent form of order condition in a discrete form according to this theorem. Now, as we saw in the definition of the method is implicit method because of this matrix A. So, according to the structure of the matrix A, we can reduce the computational effort for the solution of this method. Of course, if we choose the matrix A to be a lower triangular matrix, we can solve the internal stages equation in m successive steps with only a k-dimensional system to be solved at each step, where k is the dimension of the function of the problem. If, in addition, we impose that this matrix has one-point spectrum, we can further decrease the computational cost by the storage of the LU factorization of the Jacobian in solving the nonlinear system by means of Newton-type iterations. And also, if the matrix A is diagonal, we can solve the system in parallel. Of course, when we impose this constraint on the structure of the matrix, we cannot impose all the collocation or interpolation conditions. We need to relax some of them. That's why we don't talk about collocation, but about almost collocation. And also we need to obtain a small order. So we cannot achieve 2m, but we need to decrease the order of convergence. So we consider these three types of methods, and if the matrix is a lower A is a lower triangular, we have to impose that the functional beta j in the abscissa point Ci should be equal 0 when A is less than j. When the matrix is singly lower triangular, we need to impose the same condition, but in addition that all the elements on the diagonal should be the same. While if the matrix is a diagonal one, we have to impose that beta j in Ci is 0 for I different to j. We can write the functions beta in this way. The first one in case of GLMT and GLMS, and the second one in case of GLMD. And they both depend on this function omega, this polynomial omega, which is a polynomial of degree r minus m plus 1. So in order to find this function of beta, we need to find the values of these coefficients mu kj, and we can determine that both using order condition, the one that we can use, or the other ones can be considered as free parameters, which can be found by performing Schur analysis in order to find unstable methods. So here I present some examples of methods with 2 internal stages and 3 external ones. So m equal 2 and r equal 3. As we see, this is the Butcher array of the method, and we find the values of beta, as I said previously, and the values of the functions alpha according to order conditions. So from this the equation 5 of order conditions. We do the same in the case of GLMS. But in this case, the elements on the diagonal of the matrix A are the same, and we do the same analysis in the case of GLMD. Here we found the regions of stability in the C1, C2 plane. These regions are obtained by performing the Shor criterion. As we see, more constraint we impose in the last figure, smaller is the region of stability. And we present an example by choosing these values for the abscissa points. And of course, there are in the region of stability. And this is the Butcher array in the first case. This is in the second one, and this is in the third one. We test these methods on a test problem. We consider the Protero-Robinson problem, which is stiff when lambda is very small. So, for example, when lambda is minus 10 to 6. And we can see that we confirm the order, because the theoretical order is 3, while we see that the experimental order is bigger, is about 4. And even if we impose more strictly condition, this order is preserved, even if the error in the final step point in case of GLMD is a little bigger. And we can compare the last method with the Gaussian-Runge-Gutta method, which is a method that which have order of convergence 4, but uniform order of convergence 2. In fact, it suffers from order reduction, and when we impose that when we use this problem with lambda equals to minus 10 to 6, so the problem is stiff, the order of this method is of course bigger, is smaller, and the error too. So we have defined this type of method in the case of GLMD, which is suitable for parallel computation. So the computational cost can be reduced, and the order is preserved. In order the introduced method have uniform order of convergence.
Can you please mute all of the speakers?
Thank you.
Apart from the speaker. It's okay, Professor Maria.
Okay.
Sorry.
So they don't suffer from order reduction. We have experimentally confirmed the theoretical order, and also future work will address the construction of this method, but not with polynomials, but with other types of function bases, like trigonometrical ones. And also, we can try to apply the same technique to other type of problems, such as PDEs, oscillatory problems, integral differential equation, fractional equation, and stochastic equation. This is some of the reference used in the work, and thanks for your attention.
Thank you very much for the presentation, Professor Maria. Would you like to ask any questions? If not, I would like to ask one. Yes. Can we please go back to the problem, Protero-Robinson problem?
Yes.
No, the example. In that example, you presented the results for a specific value of lambda, minus 10 to the power 6. What is the effect of lambda on the problem? Because we only see one table. Did you differ the values of lambda to see how it affects?
Yes, because when lambda is smaller is lambda, more stiff is the problem. So we choose this value because for this value the problem is stiff. If we choose, for example, minus 10 to 3, we still have the same analogous value for these methods, but for example, the Gaussian-Runge-Gutta method has order 4. Because in that case, it is not stiff. While in case of lambda equal to minus 10 to 6, there is stiffness. So there is order reduction in Gaussian-Runge-Gutta method, while in our method, no, there isn't. So that's why we have chosen this particular value. But of course, we can use different values to smaller too, because the method doesn't suffer from order reduction.
Okay, thank you. One more question. In this table, we can clearly see from the error that the Runge-Kutta method gives poor results. And did you compare the run times, the CPU times, to see if your method is quicker than the Runge-Kutta method or not?
No, we don't in this work, because the goal is to try to written in parallel this method, because this method is suitable for parallel computation. So it's also, yes, a future work that we want to try to compare the CPU's times. But of course, the development of the method takes less time. Is one respect to these other ones, but we haven't yet computed it in parallel.
Okay, so thank you very much.
You're welcome
for your presentation.
Just a moment. Okay.
Okay. So our next presentation is about characterizing and analyzing the relation between bind packing problem and tabu search algorithm. The authors are Vanessa Landero, David Rose, Joaquin Pares, Laura Cruz, and Carlo Colasos Morales. And sorry again for the name pronunciations. And,
no problem.
Who is going to present the work?
Okay. I'm going to share my screen. Okay, you can see my presentation?
Yes, Professor Vanessa, we do see.
Okay. And this? Okay. Hi, good morning. My name is Vanessa Landero Nájera, and I am from Mexico. And I will introduce you my paper characterizing and analyzing the relation between bit packing problem and tabu search algorithm. My workplace, and I will present you a brief contents of my paper. We begin with an introduction. So, when we have some problem, the principal objective is to give the best solution to this problem. So, so need we to apply some algorithm, more specifically, approximation algorithm to optimization problems, okay? The relation between problem and approximation algorithm has been characterized by features or factors from problem or from algorithm, sometimes from both. So also this relation has been analyzed for selecting the most indicated algorithm. However, it is better to explain algorithm performance behavior besides predicting. This explanation depends on analyzing and understanding factors or features that can affect it. Okay, this table shows you the before mentioned. In this paper we propose formal characterization for relation, problem, and algorithm, including factors from problem and factors from algorithm, and considering also algorithm logical structure. So the analysis proposed on this paper is to understand, explain, and this relation between problem and algorithm and improve the performance algorithm. For that, we begin to formulate this problem statement. There are instances for a specific problem, I5, I7, and we have some algorithm that this algorithm was superior for problem instances subset and was inferior for solving other instances, okay? And the question is why? Why this algorithm was superior for solving this problem instances subset, and why was this algorithm was inferior for solving other instances, okay? For that, one possible solution can be mechanism M with input a set F with values of problem features, a set B with values of algorithm features, and a set B with values of algorithm performance. So also these mechanisms M with output a relation model R. So where algorithm performance as domination region or inferior region is described by some function D, okay? There are problem features described by variables B and C. There are algorithm features described by variables X and Y, and there are some relations, okay? And this model R is a directed graph, okay? And this directed graph can be interpreted as causal if all relations accomplish with faithfulness, minimality, and Markov conditions. If these model are accomplished with these conditions, it can be interpreted as causal model and the relation as cause effect. So if we have all these, we can solve the before problem statement. So, but there may be other models, R2, R3, so as figure that cannot solve the before problem statement, okay? In this paper, we propose a composite function for characterizing the relation between problem and algorithm, for building a causal model R with these properties, and for solving the before problem statement. Okay, this composite function was developed through case studies for bin packing problem and taboo search algorithm. Each case of study considered two variants of taboo search algorithm where there is some logical part different from this. For example, for case one, the procedure to fix taboo size can be static or dynamic. So, for example, case two, the procedure to generate an initial solution can be random or heuristic. And for case three, the procedure can be for building neighborhood using one method or several methods. So for each case, for each study case, we select randomly one algorithm for analyzing. We considered or propose variables for describing problem features and describing algorithm features. Also, we considered other variables known as scientific community as metrics. These metrics are correlation length and correlation coefficient. So the proposed composite function was developed through these two scenarios. So we can see in figure B, these metrics were not causes direct to performance algorithm. So we can see your A, that our post describe problem features and algorithm features were causes direct to algorithm performance, okay? And the interest relation were estimated and interpreted for each study case, okay? And we could understand why the algorithm was superior for problem instances subset with certain properties of problem structure, okay? So why is superior with some logical design and with some behavior during its searching, okay? So also we could understand why not this algorithm or why this algorithm was inferior for solving other instances with other properties. The discovered knowledge.
Professor Vanessa, sorry to disturb you, but can we conclude in 2 or 3 minutes?
Okay, see.
We are running out of time.
The discovered knowledge was used to modify the algorithm, more specifically the logical part in fixed to taboo size. So it means when the taboo search algorithm were executing, it adapts to instance properties for solving better that instance. After experimentation, this algorithm or this new algorithm was superior and its performance was the best, was the best. So the same procedure was for other case studies. Okay. The results of experimentation of these new algorithms were validated, developing Wilcoxon statistical test, okay? And we obtained that there is a significant difference between values of solution quality. So, as conclusion, this paper presents a formulation of problem of why algorithm is better to solve a subset of problem instances than others. A composite function is proposed for characterizing relation between problem and algorithm and solve the formulated problem. And case studies on bin packing problem in taboo search algorithm were developing through proposed function and features that describing problem structure and algorithm searching fluctuation. Also considering logical design and algorithm performance. So generated causal models allowed understand relation between problem algorithm, redesign the algorithm for adapting to problem instances and improving its performance. As future work, we continue analyze the other algorithms and other problems, and it is all. Thanks for your attention.
Thank you for your presentation. As we are running out of time, can I have the questions quickly, if there is one? If not, let's move to the last talk, which is about efficient speed up of radial basis functions approximation and interpolation formula evaluation. The authors are Michael Smolik and Vaclav Skala. And who is going to present the work today?
Me, Michal Smolik.
Okay.
Can you hear me?
Michal?
Yes.
Professor Michal, we are listening to you. we can see your presentation.
That cannot
Okay,
solve.
so hello everybody. I would like to talk today about my paper, which is called Efficient Speedup of Radial Basis Functions Approximation and Interpolation Formula Evaluation. First of all, this paper presents a method for efficient radial basis functions evaluation, and especially if compactly supported or local radial basis functions are used. Reason for this is that local radial basis functions have only limited influence, so this means that they are valid only for some limited area. And right now I should talk about radial basis functions just to give you some idea of what this is about. So radial basis functions, it's a meshless technique for interpolation and approximation as well. And if we have some scattered data as the input, then we can perform the approximation or the interpolation using radial basis functions. And the formula for the final interpolation or approximation function is exactly this one. It's just some sum of weighted functions where lambda j are some weights, m is the number of radial basis functions, and phi is the radial basis function. And you can see that this radial basis function is only depends on the distance between 2 points. So in 2 dimension and in 3 dimension, the radial basis function looks exactly the same. So, and if we have some known values and we want to compute the radial basis function formula, then we have these equations. We have one equation for each input point, and as the result, we end up with some linear system of equations. A times lambda is equal to some values. We have some different types of radial basis functions. We can have the local radial basis functions or the global radial basis functions. The global radial basis functions have some number for all of the values of R, but the local radial basis functions, they have some limited influence, and it means that they are valid for R equals to 0 until some maximum number, and if the distance R is more than the maximum distance, then the local function is equal to 0. And you have many of these functions as example here. So when you're doing the radial basis functions approximation or interpolation, you end up with some formula, and you want to, at the end, you want to evaluate your formula at many points. But when you are using only local radial basis functions or compactly supported radial basis functions, then they have the limited influence. So when you're doing the computation of the sum, which is shown here below, then you compute the radial basis function usually for all of the points, and you compute all the radial basis functions. But many or most of the radial basis functions are always equal to 0 when you are using local radial basis functions. So it doesn't make any sense to compute all of the radial basis functions, and you should compute only this that should be different than 0. So you can see that there is some maximum distance where the radial basis function can have some number different than 0, and in this area it makes sense to evaluate the radial basis function. If the distance is more than this distance, then it doesn't make any sense to evaluate the radial basis functions, as it will be 0. So we would like to propose some approach how to find out which radial basis functions we should evaluate and which one we should skip during the evaluation process. For this, we can use the space subdivision of radial basis functions. each radial basis functions has some maximum distance, as I showed you before. So we can create some grid, which is G times G, and the size of each cell is R max times R max. And on the right picture, you can see what is the meaning of this size of this cell. When you have one point which is exactly in the corner of this cell, then the maximum influence of this radial basis function is exactly this circle, and this means that this radial basis function covers these 4 squares. So if you want to evaluate one point which is exactly in this cell, then this means that you need to evaluate only this radial basis functions that are in these 9 cells in 2 dimensions. Radial basis function, which is, for example, here, doesn't make any sense to evaluate because the distance from this radial basis functions to some point in this gray area will be more than R max, and thus the radial basis function will be 0. So I have some theoretical speedup for the evaluation of radial basis function. When you're doing the standard evaluation of function using radial basis function, then it has the time complexity of OM, where M is the number of radial basis functions. So it means that you evaluate all of the radial basis functions and then compute the weighted sum. However, our proposed approach has lower time complexity, and this time complexity can be showed as here. It's 3 up to D, where D is the dimension of the problem. So in 2 dimensions, you have 3 up to 2, so it means 9. So you have to evaluate just 9 cells, and then it's multiplied by M divided by G, where M is the number of radial basis function and G is the number of cells that we are divided our input data. So the expected speedup of our proposed algorithm to the standard one is as shown here, and we can simplify it just that it's the number of cells divided by the number of cells that we need to evaluate the radial basis functions. So you can see that the speedup is quite high, and we are computing the evaluation of the radial basis functions usually in thousands and thousands or millions of points. So the speedup is really important. And you can see in this graph how big is the theoretical speedup of the evaluation of radial basis function in 2 dimensions and 3 dimensions. And you can see that even when you are dividing the radial basis functions into, for example, just 30 times 30 cells, so it means 900 cells, then in 2 dimensions the speedup is already 100, which is quite a lot. Then we also tested the speedup of our proposed approach on some real and synthetic datasets. We used 2 types of real datasets. This one is some part of Alps, and this one is also some real datasets which consist of 756,000 points. And we divided this input points and the radial basis functions into several number of cells, which are shown here. And on the right side, you can see which was the measured speedup, and you can see that the speedup for real data sets was for the smaller one 140, and for the bigger one it was 800. So it's quite high speedup, and the algorithm is really easy to implement. So we also have the measurements of the speedup for 3 dimensions when you are evaluating the radial basis functions, and you can again see that the speed up for higher number of radial basis functions is also quite high. And when you have the same number, for example, of radial basis functions, then you can obviously have different numbers of cells. It depends on you how you will divide the grid. And if you choose higher number of cells, then the speed up will be obviously higher as well. So for the conclusion, we have presented a new approach for speeding up the evaluation of radial basis functions, and the proposed approach uses the space subdivision to select only the appropriate locations of radial basis functions that are used to evaluate the radial basis function, and you do not need to compute or evaluate the radial basis functions that will be zero. This proposed approach is very easy to implement and can be used for any dimension, and the proposed approach has a significant speed up compared to the standard one evaluation of radial basis function. So that's all. Thank you very much. And
thank you very much, Professor Mikkel, for your presentation. Would you like to ask any questions? May I ask one?
Yes.
We have a few minutes. In the beginning of the presentation, you listed a few radial basis functions, local and global ones. I see 5 here. Did you try all of these local radial basis functions, or did you just focus on one of them?
We performed these tests I showed you with this radial basis function with V5.
Okay.
But usually it doesn't really matter which function you will use, because you will reduce the number of radial basis functions that you need to compute. So the speed up should be exactly the same when you're using V1 or when you're using V9 or V10. It doesn't really matter. The speed up will be exactly the same.
Okay, thank you very much.
Will be different.
I was wondering about that. And one more question in terms of numerical point of view. In the previous slide, I guess you said that you end up with a linear or a system of equations. Yes, linear. A lambda equals to h. Are there any special properties of the matrix A here? Like, is it a sparse, three-diagonal, full, or anything special about this matrix?
Yes, when using the local radial basis functions, then most of these radial basis functions are equal to 0. So this matrix A is really sparse. And
it's a sparse one. Yeah. Okay, and so you didn't see any computational problems while calculating this linear system?
Yeah, of course, if these matrices are higher, then you have some big problems with the conditionality of this matrix. And,
okay.
But you have to solve it somehow. But for this problem, you do not really need to. You need to solve the matrix, but the proposed approach is talking about the evaluation. So it's just the step after you solve this matrix and you end up with some lambda values, and you want to evaluate this function. Then this approach is for this.
Okay, so thank you very much. I would like to thank all of the participants and the speakers. Thank you very much for attending our session and our conference. We hope to see you all in the next year's conference. I wish you a very good day. Have a nice day and goodbye.
Have a nice day too. Bye.
Bye. Bye.
Bye.
Good morning, everyone. I'm Beniamino Morgante. I will chair this session, general track session.
Good morning, Dr. Morgante.
I suppose that you are one of the speakers, no?
Yes, I'm the first one, actually. The first presentation.
Yes, first presentation, but you are...
Mizak Ketabdari.
Okay, perfect. Perfect. Okay. Other speakers?
Yes, I'm Daisuke Takahashi, second speaker.
Okay, you are one, just you. I don't have to highlight you among the other authors.
I'm here.
Yes. Just two speakers? No, I hope that other will come. Joao Gabriel Rocha. Are you probably the third speaker, I suppose?
I'm okay. I am presentation 3 and 4.
Ah, okay. And your name is Joao Gabriel Rocha Silva?
Yes, I am.
Okay, no, just for... Because in one case you are the complete name. In the second case you are just Joao Silva. That's why, because probably the second paper has not submitted by you, and who submits the paper probably it was a little bit lazy and don't want to write all your name in this case. Okay, this means that we have the complete square of the speaker. In my opinion, we can start in this case.
Okay.
I hope that the assistant in the room is here and he can start also the recording. No, probably. Raffaele, are you here?
Yes.
We can start. You can start to the streaming on YouTube if you want.
No, we are already live.
Okay, we can start. It means we can start. Okay. Welcome to the general track session. I ask to Misag Keta Badari to have the first presentation with Emanuele Toraldo and Maurizio Crispino, numerical risk analysis of the impact of meteorological condition on probability of airport runaway excursion accidents. You have 10 minutes, 8 minutes for presentation and 2 minutes for questions.
Okay, sure. I try my best to...
Okay, thank you.
On the time. Can you see my screen?
Yes.
Okay,
perfectly. Perfect.
Perfect. Good morning, everybody. My name is Mizak Ketabdari. I'm a postdoctoral researcher at Politecnico di Milano. With Professor Emanuele Toraldo and Professor Maurizio Crispino, we developed a study on numerical risk analysis of the impact of meteorological conditions on probability of airport runway excursion accidents. The scope of our study is to identify the impact of different weather components on the frequency of runway excursion accidents. This study is done in two sections, different methodologies. The first part is a statistical analysis of the registered accident for a time span of 5 years. That we collect this data from NTSB, National Transport Safety Board database. And the output is to identify specific weather components that have crucial impact on the frequency of runway-related accidents. On the second part, we did numerical risk analysis. So we select 3 case study airports with unique climate characteristic. And in order to do sensitivity analysis, we select also 3 different weather scenarios. And finally, we use RSARA and LRSARA software that simulate aircraft ground operation. And also we did further sensitivity analysis. So I would start with the first section of the study, which is a statistical sensitivity analysis. Runway-related accident can be divided into 2 different categories. The first one would be incursions, which means all the accidents occur inside the runway, such as collision with obstacle or collision with another aircraft. And the second division is excursions, which means all the accidents occur outside the runway area, which can be takeoff overrun, takeoff veer off, landing overrun, landing undershoot, and landing veer off, as presented in the pictures. The focus of our study is on excursion type of events, since we collected registered accident for a period of 15 years from 4 major aviation databases, which are Airbus, Boeing, National Transport Safety Board, NTSB, and also Aviation Safety Network, ASN. The results shows us that among all accidents that occur in aviation industry, 25% are runway-related accidents. And from this 25%, 97% are dedicated to excursion accident, runway excursion, and only 3% are runway incursion. That's why the focus of our study is on excursion accidents, since they are most frequent runway-related accidents. According to the availability of the data and the appropriate way of recording and registering of the accident, we choose NTSB database out of those 4 databases that I mentioned before, and as a foundation of our study. And we collect the registered accident for 5 years, from year 2003 to 2007. And we totally collect 8,657 accidents from all over the world. And we understand out of this number, 20% are those accidents that trigger because of a weather condition, because of a meteorological condition. We break down this data and we understand that for this 20%, there are 2,230 citations of meteorological subject modifier. We break down this weather component into each specific component, and we understand among all these components, wind with approximately 50% citation and visibility ceiling with approximately 24% can be considered as dominant contributing parameters in weather triggered accident compared to the other components. So as long as we understand wind and visibility can be most catastrophic, we studied them separately, and first one would be the wind. We again break down the wind into its components, and we understand that gusts, crosswind, and tailwind are accounting for approximately 85% of wind-cited accidents. We did the same thing for visibility and ceiling, and we understand that low ceiling, cloud, and fog, so it would be heavy cloud and heavy fog, are the principal contributing factor that accounts for approximately 86% of visibility ceiling cited accidents. So the data that we achieved from this first part, that are the wind components, in particular gust, crosswind, tailwind, and visibility ceiling components, in particular low ceiling, clouds, and fog, are the main principal parameters that can trigger one runway excursion accident. So according to the result obtained from this part, we defined different weather case scenarios for the next step, next part of our study, which is numerical risk analysis. So now I'm going to explain this part. 3 specific airports are selected according to their unique climate characteristic in order to carry out simulation and further sensitivity analysis. So now we want to do the numerical risk analysis. We choose 3 specific airports with different climate characteristic, CS1 or A1, A2, A3, and with different historical weather data, runway and safety area dimensions, and annual traffic growth rate. In order to do the simulation and run the simulation, we need initial inputs. That's the principal ones are historical operational data. These historical operational data are all those accidents, incidents that occurred in that specific airport that we selected for an interval of at least 1 year. So we collect the data of the registered accident for 1 year for these 3 specific airports. And also we need historical weather data as a second input. That should be that these data should be synced with the historical operational data. So again, we collect the weather data for the same year as the accident studied year, I mean. Plus, we need airport characteristics such as above sea level elevation, annual traffic growth rate, the type of flight, is it commercial, is it general aviation, cargo, and etc. We need to set risk criteria for the study, and we choose 10-6 as the target level of safety of this study, which means 1 failure in 1 million operation. We need to also define runway configuration, such as runway designation, dimension, landing distance available, and etc. Last but not least, we need runway safety area geometry and obstacle. We need to design and define this geometry and obstacle. That we did it based on Visual Basic Excel-based spreadsheet. And as you can see, each color, and we should do it, I mean, in order to do the simulation for each runway end and for each airport. So as you can see, each color is standing for a specific type of obstacle. So if that obstacle is fragile or if it is solid, so the consequences can be remote or can be catastrophic. As you can see, the green is a stand for the grass, the yellow is stand for instrumental landing system, the pink is a stand for unpaved area, the gray is a stand for paved area, and the red is a stand for all those solid obstacle that would lead to catastrophic consequences, such as mountain, such as water, such as cliff, and such as all other type of limitation, restriction that one runway can have. The methodology, the formula of this study is based on Airport Cooperative Research Program, ACRP, that this formula is evaluating the probability of occurrence of one specific event in the presence of different weather components, such as ceiling, visibility, crosswind, or precipitation with different levels, actually. And the result out of this simulation would be, we can have lots of different results, but the main result that we need are average frequency of accident outside runway safety area, average number of years expected between accident, and percentage of movement with risk higher than adopted target level of safety. Meanwhile, that we did the simulation, we also defined 2 extra weather scenarios in order to identify and evaluate better the impact of each weather component. So we define favorable or best weather case scenario, which you should select. These results, selection is based on the first part of the study, and you should select perfect visibility, mild air temperature, no extreme cloud coverage, no precipitation, etc. An unfavorable or worst weather case scenario with extreme form of precipitation, presence of dense fog, heavy wind gusts, thunderstorm, and etc. And the third scenario would be the actual weather simulation of the actual weather condition, actual weather data that collected. So the result also would be, again, we achieve different kind of result, but because of the because it's out of the patience of this presentation, I just provide here one schematic result, which is the meteorological condition sensitivity analysis for case study number 2. As you can see on the graph, We did it for different runway-related hazards, such as landing overrun, takeoff overrun, landing undershoot, landing veer off, and takeoff veer off. And the result shows us that weather conditions have more critical impact on overrun and undershoot excursion event. It can be up to 3 orders of magnitude, rather than veer off accident, which can be only 1 order of magnitude, and it can be seen on the graph that divergence of veer off probability values are less than others. Plus, there is a difference of 1 order of magnitude between the extreme weather scenario and the normal state-of-the-art condition of landing-related events. Plus, average probability of all types of runway excursion events undergo significant alteration by moving from unfavorable or worst weather case scenario to favorable and best weather case scenario, except for takeoff veer off. It means that takeoff veer off is not affected the same as other runway related accident by weather conditions. And last, according to the simulator software, meteorological components such as crosswind, rain, ice, snow, and in general wet pavement for the runway are the principal factors that cause unfavorable weather conditions and can increase the chance of a specific accident up to 3 orders of magnitude, which is really tremendous in the risk assessment. That's it. Thank you for your attention. I hope you enjoy, and if you have any question, I'm available.
Professor Morganti, your microphone is turned off.
Okay, sorry. Thank you, Misag.
You're welcome.
Questions? There are questions? Questions? Okay, just one. You considered just sensitivity analysis. Have you thought to consider all kind of analysis for manipulate this data in order to normally expert in model, no, in analyzing data. If you try to simulate this data with another model, probably the results are not the same. In order to be sure, because in this case it's important for the life of people, no. It's important to have 2, 3, 4 model, and if you have comparable results, it's good to
absolutely. Actually,
or if it's your intention to do this simulation in future, I don't know.
Actually, right now we are making another model, because this model is the model that proposed by HCRP, and we try to evaluate and validate their results, I mean, for us. But now we are also providing another model, which is writing based on finite elements situation, modellazione. And we are trying to provide another model by considering other type of components such as runway configuration, not only the weather parameter, because also if you have in this scenario that we talked about, we didn't consider the mitigation strategy, such as the runway and safety area dimension, and also if there is any installation such as EMAS, engineering material arresting system, in that area to reduce the risk. Therefore, we are developing another methodology right now, and for sure it would be in another study. First our result, and then another study would be the comparison between these 2 methodologies in order to find out which would fit better with the condition of your selected case studies.
Okay, thank you for your presentation. When you develop other study, please tell me, because it's quite interesting. It's quite interesting your presentation, and also I suggest, because there are several special issues related to transport, 2 on Elsevier journal and 2 on MDPI journal.
Yes.
After the conference, if you send an email to the organizer, probably you can do an extended version of your paper.
It would be a pleasure. It would be a pleasure. Thank you so much.
Okay, you are welcome. Okay, we can go to the next speaker. Daisuke Takahashi. Fast multiply Montgomery multiplication using Intel AVU X512 EIFMA instruction. I repeat that you have 10 minutes, 8 minutes for the presentation and 2 for questions.
Okay. Can you see my screen?
No, I see
no.
just D and T.
Okay.
Okay, no, it's okay. Now it's okay.
Okay, thank you. Thank you for introduction. My name is Daisuke Takahashi from University of Tsukuba. Today, I'd like to talk about fast multiple Montgomery multiplications using Intel AVX 512 IFMA instructions. So, modular multiplication is widely used in fields such as computer algebra and cryptography. It includes modular operations, which are slow because they involve an integer division process. Montgomery multiplication avoids the integer division process. Modern processors support single instruction multiple data, SIMD, vector instructions. The Intel Advanced Vector Extensions 512 is a 512-bit vector instruction set. As for related works, the Montgomery multiplication algorithm that use vector instructions have been proposed. First, modular squaring with Intel AVX 512 IFMA, integer fused multiply add, has been proposed. Vector instructions have also been used to compute multiple Montgomery multiplications in parallel. For multiple Montgomery multiplications, implementations based on Intel streaming SIMD extensions to instructions and the cell processor have been proposed. So let me talk about the objectives. Montgomery multiplication is usually performed on integers of several hundred bits or more. However, we consider the case of 52 bits or fewer. So multiple Montgomery multiplications with such numbers of bits are used in the modular fast Fourier transform, FFT. The two best of our knowledge, there are no existing implementations of multiple Montgomery multiplications using Intel AVX 512 IFMA instructions. So we propose such an implementation and evaluate its performance. This slide shows modified Montgomery multiplication algorithm. In this algorithm, so inputs are A and B and N, and output C is A times B times beta inverse, modulo N. When beta is a power of 2, integer divisions can be replaced by shift operations. So lines 3 and 4 and 5 are modified from the original Montgomery multiplication. This modification avoids double word addition and shift operation. And the Intel AVX 512 IFMA instructions are supported by the Cannon Lake and Ice Lake microarchitectures, and will be supported by the Tiger Lake microarchitecture. The Intel AVX 512 IFMA instruction set supports the VPM added 52 LUQ and VPM added 52 HUQ instructions, which multiply 52-bit unsigned integers and produce the low and high halves, respectively, over 104-bit intermediate results. These halves are added to 64-bit accumulators. If the Montgomery multiplication operand is 52-bit or fewer, beta is equal to the 50 seconds can be set in algorithm by using the Intel AVX 512 IFMA instructions. So this slide shows the vectorized multiple Montgomery multiplications of 52-bit integers using Intel AVX 512 intrinsics. So in this program, each intrinsic corresponds to the Intel AVX 512 instructions. And let me talk about performance results. So for performance evaluation, comparison among multiple 52-bit Montgomery multiplications using Intel AVX 512 IFMA instructions and multiple 62-bit Montgomery multiplications by using Intel AVX 512 foundation instructions. And the last one is multiple 64-bit Montgomery multiplications using the Intel 64 scalar instructions. Such multiple Montgomery multiplication was performed on an Intel Core i3-8121U processor, which is the only processor based on the Cannon Lake microarchitecture. So the batch size of Montgomery multiplication was varied 64 to 1024. Each batch of Montgomery multiplications was executed 1 million times. The number of Montgomery multiplication per second was calculated based on the average elapsed time. So this slide shows the performance of multiple Montgomery multiplications using various instructions. So x-axis shows the batch size, and y-axis shows the number of Montgomery multiplication per second. And the blue line shows that the Intel 64 instructions, and red line shows that the AVX 512 foundation instruction. And the green line shows that the proposed implementation of the AVX 512 IFMA instructions. So you can see from this graph that when the batch size was the 128, the proposed implementation using the Intel AVX 512 IFMA instructions was about the 12 times to the Intel 64 instructions, and about 4.3 times faster than the implementation of the AVX 512F instruction on the Intel Core i3-8121U processor. So the reason for this is that while the implementation using Intel 64 instructions calculates on integer at a time, the implementation using the Intel AVX 512 IFMA instructions calculates 8 integers simultaneously. Furthermore, the number of instructions is smaller in the implementation using Intel AVX 512 IFMA instructions than the implementation using AVX 512 foundation instructions. So, in conclusion, we proposed a first implementation of multiple Montgomery multiplications using Intel AVX 512 IFMA instructions. The proposed implementation is based on a modified Montgomery multiplication algorithm. For Montgomery multiplication operand with 50 clear, the proposed implementation using Intel AVX 512 IFMA instruction outperforms implementations using Intel 64 and Intel AVX 512F instructions on the Intel Core i3-8121U processor. Our future work is to demonstrate the effectiveness of the proposed implementation on other processors that support the Intel AVX 512 IFM instructions. That's all. Thank you for your attention.
Okay. Thank you, Daisuk, for your very interesting presentation. Questions? Just a small question. But in our future, you have are supposed to have other similar experience in order to improve, because it's quite impressive that you can have you improved the performance of with the 52 bits rather than other processor with the 64 bits. In this case, have you thought to do this, to try to do this with other chips or not? What is your idea about this?
Sorry? Repeat your question.
No, because it's quite impressive what you explained, no? About the possibility to improve the performance in this case with 52 bits faster than 64 bits in this case. Have you? I understand your conclusion, no? Your future, but are you an idea to repeat this experience with other in other similar cases, or just in this case, or not?
So I have already tested our algorithm to the other processors.
Okay. Other questions? Okay, we can go. Thank you again, Daisuk, for your presentation. You can go to the third and at the same time fourth speaker, because he has two presentations. The first presentation is João Gabriel Rocha Silva, Ricardo Silva Campos, Carolina Ribeiro Xavier, and Rodrigo Weber dos Santos. Simplified models for electromechanics of cardiac myocyte. Okay, for both presentation, you have 10 minutes, 8 minutes for presentation, and 2 minutes for question. Obviously, I will introduce you again for the second presentation.
Okay. 1 minute, please.
Yes.
Can you see my screen?
Yes, now. Let's see your screen. No, not me. Don't show me, but your presentation.
Okay, can you see my screen?
Yes, now.
Yes, no?
Okay, perfectly. You can start.
Are you okay?
Yes, yes, perfect. You can start.
Okay. Good morning, everyone. My name is João Gabriel. I am a professor at the Federal Institute of Education, Science and Technology of Mato Grosso, Pontes de Lacerda, Brazil. This work is part of my study entitled Simplified Models for Cardiac Electromechanics of Myocytes. My presentation is divided into following sections: background and motivation, preliminary studies, proposed models and results, the creation process of Model C, and finally conclusion and future works. Mathematical modeling is an important tool for studying different phenomena, among them the behavior of the heart. However, more realistic simulations can take a lot of time. In this work, we studied simplified and complex models in order to propose an electromechanical coupling of myocytes. the proposal and low computational cost and good qualitative results. This figure shows a change in a coupled electromechanical model where the electrical part comes from the 10-Tusher model with 19 ordinary differential equations, and the mechanical part of the model presented by Rice with 11 ordinary differential equations and 45 algebraic equations. This model is used as a reference for the project because it has a simulation compared to experimental data. This is a simplified coupled model supported by only one differential equation for electrical activity and another for mechanics. This model is based on these works. We can verify that due to the fact of the low number of equations for the representations, the results, especially for the mechanical activity, are far from the experimental ones, mainly when compared with the models of the previous slide. After the analysis of these models, our objective is to present two new models for electromechanical coupling of cardiomyocytes. These models must be qualitatively satisfactory for the contraction based on the 10-Tusher Rice model, but low computational cost. One of models, Model A, is based on adaptations of the contraction equations presented by Nash-Pavlov, and B uses Elincourt equations, variant of Nash-Pavlov equations. In both of the 10-Tusher model, excitation was used. First of all, we only coupled the models using the parameter presented in their respective articles, and the parameters are shown below, and TA refers to active force. In the same way, Model B, changing only the equation of active force. The parameters are shown below. In these figures, models A and B are attacked. It is possible to see the direct coupling does not present a suitable behavior for the active force in neither of the two proposals. This phenomenon can be related to values of unsuitable parameter, making the active force tend to behavior of the action potential. Here and here. Then we put the parameters of the models in a genetic algorithm in order to qualitatively improve the behavior of the active force. The objective is to approximate the AF hour model to the 10-Tusher Rice model. The parameters to be adjusted in genetic algorithm are shown in red. The figure shows the results obtained using the genetic algorithm. It is possible to verify that the active force presented better results when compared to the first step of the model creation process, aiming at an approximation to the active force of the example model. However, the quality of the reproduction is still poor, especially for Model B, which still tends to action potential in parts of its evolution. To improve the model, we change KTA from a constant value to a function of V. Furthermore, we added a new equation to represent the active force considering the delay between stimulus and the contractive response, and this equation and this equation, ODE and algebraic equation. The adaptations in Model B were the same of Model A, except in the velocity control, specified by equation 9 in here. This figure presents the result obtained for 30 steps of the development Model A and Model B post-use genetic algorithm. it is possible to verify a significant increase in the quality in the reproduction of the active force in both models when compared to curve of complex realistic model, with a small problem that consisting of the mediation set of post-stimulus contraction, which does not occur in biology. Here's a problem and problem. Two models, both models, sorry. Last stage consists in the correction in the multiplier of the differential equation proposed for delay due to its still inadequate behavior. Thus, the term multiplier is no longer the same as the differential equation for TAI. It breaks down into a function defined by TAI dependent parts and the action potential. The fully developed Model A and Model B is given in equations shown. For the last time, after this consideration and modification presented in this phase, the parameters of the models were submitted and to the GA developed in order to minimize the difference between the curves of the complex model and the simplified model we proposed. As can be seen in figure, the proposed models were able to reproduce with excellent quality the active force that generates the contraction based on comparison of the models, a complex models with numerous considerations. A phenomenon observed based on the development of models A and B is that for both models, the smaller the variation of multiplier E0V, the better the result of the reproduction of activity force. Then we replace a function for a constant. Here's a constant. In figures, the active forces show for the electromechanical model C from the parameter adjustment performed by the GA. It is possible to observe that just like the previous model, this model was also able to reproduce the active force coming from a more complex model. However, in an ever simpler way, elimination one algebraic equation and two parameters in relation to model A and three parameters in relation to model B. Conclusion and future works. The models obtain good solution for the contraction. It was effective to reduce the computational cost, decreasing about 9 differential equations and more than 40 algebraic. In future works, we proposed testing the model using more stimulus of action potential. Thank you for attention. Thank you very much.
Thank you, Joao. You can probably it's better to see you, not me. Probably you can. It's better for you to have the second presentation, and we can collect question at the end of your second presentation. Second presentation is a paper written by Ricardo Campos, Joao Gabriel Rocha Silva, Elio Barbosa, and Rodrigo Santos, electronic effect on action potential dispersion with the cellular automata. Okay.
Can you see my presentation?
Yes, perfect. You can start.
Okay. This work is electrotonic effect on action potential dispersion with cellular automata. The first author is Ricardo Campos, but I will present it. Add more realism to our cellular automata for simulating the heart function. Isolated cells have a different behavior, When connected in tissue, their interaction may change these features. Electrotronic effect, homogenization, the repolarization dispersion. AP morphology change during simulation, all cells to return to their resting potential at the same time, regardless of their initial action potential duration, in order to avoid understation. About the heart, pumping blood, heartbeat rhythm controlled by an electrical wave. Same regions in the heart tissue start the wave that propagates in woolly organ. Complex phenomenon is depending on your concentration, cell membrane capacitance, and so on. The heart tissue has cells with different features that change in different regions such as the ventricle and atria. The action potential has different durations for each type of cell. However, neighbor cells interact and influence each other. Traditional cardiac models use cell modeled as electrical circuits. Example, membranes, capacitors, separation different charges, ions channels, allows or not ion passing through membrane, resistor, supported for differential equations. Traditional cardiac models, spread of electricity over tissue, partial differential equation, mechanical contraction, continuum mechanic, and benefits and drawbacks. Benefits, detailed and multi-scale data, ions, proteins, cells, tissues, organs, useful for studying disease, simulating new drugs, and drawbacks, time-consuming simulation, time-consuming parameter adjusting, impractical for real-time simulations. Modeling the action potential propagation with cellular automaton, simplification, ignored some phenomena, only considered what is important to our problem, simpler equation, faster simulation. It mimics the action potential of ODE models. Example, using cellular automata. Here the grid of cells. Cells contain states, example, state white, state gray, and state black. One cell propagates its state to its neighbor, example, black and gray, according to some set of rules. Heart, propagation of electrical pulse, excitation of neighbor cells. Irregular mesh of tetrahedrons. A cell is a neighbor to another if they share at least one point along irregular shapes. This and element in black, excitation, your neighbors, H neighbors, conform this figure. Methods. AP is divided in 5 states. Initially, cell is resting. S0 and S0. Some special cells, the space markers, start the AP and then its propagation over the grid. State wave, a predetermined time and AP. Propagation rates, when stimulated and when be stimulated. S0, here, can be stimulated. S1 and S2, simulated neighbors. S3, no stimulus allowed. S4 can be stimulated by 2 or more neighbors. The present method propagates AP, but it can't change AP morphology. States time and value, predefined and constant, isolated cell behavior. A new method is proposed to emulate cells change due interaction. Example, cellular automata in active force. Active force is responsible for contraction of the tissue. It depends on the AP. AP changes calcium contraction results in the cell contraction. CA for force development, F0 in F1 when S1 in S2. Delay. Force starts at the cell stimulation. After F1, cells change states by timing. A new model is proposed to emulate cells change due interaction. Average neighborhood APD, this equation. Cell conductance, where P user-defined percent, F is percent force applied, max F deformation coupling, equation for cell conductance. New APD, zero conductance keeps APD constant, one conductance tends to equalize all APDs. Results. For evaluation our model, we configure a cut of tissue as follows. We equally divided 3 types of cell in tissue: endocardium, mid-myocardium, and epicardium. They represent respectively the intermediate and lower outliers of ventricle. They were set up with different action potential durations: 105, 250, and 160 milliseconds. The electron wave starts at endocardium at phase in plane x equals 0 for all cases. Then we manually set parameters up to simulation tissue in for different circumstances. The parameters represent the conductance of cells and action potential propagation velocity. Isolated cells. The cells in tissue have no influence of neighbors. Their conductance is 0. Poor coupling. This configuration represents U cells with poor conductance. The propagation velocity is lower. Reduced coupling. This emulated the transverse fiber directly. It has a greater conductance and velocity. Normal coupling. This represents the healthy tissue. It has a greatest conductance and velocity. The parameters were chosen in order to reproduce results obtained from the literature. In this table, we can see the action potential duration of the different types of cell at the ends of simulation. The isolated cell's configuration does not change its action potential duration, since cells are not influenced their neighbors. For pole, reduced and normal coupling, we can see the difference of final action, potential duration, and become smaller as conductance increase. This happens because the cells are influenced more each other, and therefore their action potential tends to have closer values. In the figure, the difference can be seen through the tissue. The isolated configuration contains 3 values of action potential duration, and its distribution is a discrete set of 3 values. On the other hand, the normal configuration has the smoothest curve, since their action potential duration are very similar. The intermediate case follow this tendency in being smaller as the conductive increase. This figure shows the action potential of the central cell for each type. Figure is the action potential of isolated cells. Their morphology is unchanged. It is clear that the mid cells have a longer AP duration. Figure D is the normal coupling case. It shows the mid cells with a smaller AP duration and therefore a more uniform dispersion. This means cells tend to return to their resting potential in similar times due their influence on another. So our model is able to simulation this neighbor interaction. Finally, these figures show the morphology of reduced and poorly coupled cells by their type. In reproduced coupling, we see a different gestation time for the cells because of its slower velocity. Since it has same conductance, the action potential duration also have returned to resting in similar times. However, it is not too close as the normal coupling. We see in poorly coupling that the polarization wave takes a long time to arrive at epicardium cells, since it has the slowest velocity of propagation. Conclusion, we added a new feature to our models. It adapts the action potential duration by a simple connective parameter. Our experiments successfully reproduce the results obtained in literature, fast, and 14-20 milliseconds execution time. Thank you for attention. Thank you so much.
Thank you, Joao. Question, final comment to both presentation. Now you can close your sharing screen sharing, because otherwise you show me, because or me or the other who will speak. Okay, questions? You can break the sharing screen, the screen sharing. Joao.
Okay.
Okay. Okay. Questions from the other? Final conclusions? Okay. In your first presentation, if I understand right, you reduced a lot the number of the equation, no?
Okay.
To improve the performance in this case. And how do you considered also other possibility in order to improve the performance, or not only reduce the equation but also in another way?
In FutureWorks, we attacked in time consideration. Considering time for simulation.
Yes.
Understand?
No, because the signal was lower in this case. I don't understand. Can you repeat, please?
In FutureWorks, we attacked in considering time computational time, cost time.
Yes. No, because it's obviously is a good things to reduce the equation, but it's not only the only component in improve the performance in this case. Just in this case, I ask you this, not because probably if you thought other possibility to improve the performance. No. Reduce computational time, but it's not the main problem, in my opinion. Probably can use, I don't know, other numerical methods, etc., etc., etc. No. And okay, other questions? No. Okay. We can close this very interesting session. I saw Ana Rocha. I don't know why. Probably is the next session. Okay. I thank you for participants for the very interesting presentation, and I leave my microphone to Ana Rocha for the
next session.
Okay.
Good morning.
Bye bye.
Goodbye.
Bye.
Bye. Thank you.
I leave the room.
Okay. So I think I will share now a session. So now there will be a general track session. I don't know if the speakers are already here.
Yes.
Hi.
Yes.
Yes.
You are. Sorry. So we have Mauras. I don't know if we say like this.
Yes, Murat.
Moraz Ulbrich. Is that you?
Yes.
Nice to meet you.
Nice to meet you.
The first speaker. The second speaker, Bruno.
Hello,
Bruno Alves.
I'm here.
Okay,
Nice to
morning.
meet you. Morning.
Nice to meet you too. Bom dia, parece-me. Sim?
Sim.
Darlias, the third speaker.
It's me, but I am Altay Utsenbaev.
You are, sorry?
From Kazakhstan.
You are the third speaker.
Yes, yes.
The third one. And the last one, Thomas, is
hello.
here also. Okay. So you are all here. Thank you. So let's start the general track session. The first 6th edition of the general track 1. I want to welcome you to this session and the conference, ICCSA, and I hope you are enjoying the conference. Now, the presentations will be 8 minutes each one, plus 2 minutes for questions and answers, okay? So the first one will talk about isolation-based anomaly detection for data streams using Scikit multiflow. I don't know if it says if we say like this. So the first one can start. Please share the presentation. You can share and then you can start.
Thanks. Are you seeing my presentation? My screen? Hello.
Yes, you can start.
Okay. Thank you. Hi, everyone. I am Moraz Ulbrich Togbe, and I am here to present our paper named Anomaly Detection for Data Stream based on isolation forest using Scikit multiflow. This paper is the first step of a project about Scikit multiflow, which concerns different universities. For this presentation, I will talk about the different methods for anomaly detection in streaming contests, and I will discuss about the experimental evaluation we did to approve our implementation of eForest ISD method. Anomaly detection is a specific application of machine learning which identify anomalies in the dataset in order to explain their presence. So detecting anomalies means to modelize the normal behavior in order to discover those observations which has not the common normal behavior. In the streaming data, detecting anomalies is an important issue in a variety of real-world applications. It provides information like cybersecurity attacks and can help to discover or predict disease in healthcare. It is also helpful in decision making. In the specific context of a data stream, methods have to be in single pass and in unsupervised way, fast executive, and low memory consumption. About the framework which implement anomaly detection methods, Scikit multiflow is an open source machine learning package for streaming data, which is written in Python. It complements the well-known scikit-learn, whose primary focus is batch learning. In this framework, there exists a variety of streaming methods in different domains, but in the specific domain of anomaly detection, there only exists one method, which is half-space trees. So the paper has two main contributions. First, we survey anomaly detection methods in streaming, and we classify them according to the approaches, and we highlight the advantage and drawback. In the second Second, we extended the scikit multiflow framework by adding the method eForest ASD. In the state of art, there exist many methods for anomaly detection, but not all of them are adapted for data stream contest. So we first distinguish those who are adapted for streaming contests, and we classify them according to the approach. The isolation-based approach is a recent approach, which is very suitable for data stream because it don't need to compute any density or distance to detect anomalies. This method, half space trees, is already implemented in scikit multiflow, so we decided to implement eForest ASD. Now I will explain how isolation-based work and how eForest ASD work. The isolation-based goal is to isolate data. So the abnormal data, the anomalies are quickly isolated than the normal data. And eForest is based on a forest of random and independent binary trees. Every node is split by randomly choosing one attribute and one split value. The score of the data is computing by using the average path length of the data in every tree of the random forest. So now eForest ASD work. eForest ASD is based on the sliding windows, and in every windows it computes eForest method to detect anomalies. eForest ASD also deal with concept drift by using one parameter u. So when the anomaly rate in the windows is upper than the parameter, the concept drift is detected, and the anomaly detector is updated with the current windows. In order to validate our implementation, we did different experimentation, and we compare eForest ASD and half space trees on different metrics. We use F1 score metrics, and we also consider the running time and memory size, which are very important in streaming contests. We also use 3 different data sets, which are well known in the anomaly detection array. Our implementation is open source and is available on GitHub. First, I want to note something about half space trees, is that half space trees is very different from eForest ASD because half space trees has a fixed tree depth size and cumul on each node of every tree a mass. It also splits node by using the midpoints. Our results show that eForest ASD is more accurate than half space trees, and we can also see that shuttle is perform well with a relatively small sample size, but half space trees perform well with a relatively big sample size because eForest is depending on the data set, which is in balancing. So when the sample size is high, the abnormal data are not really representative, but half space trees is independent to the data set. Because of the fact that half space trees has a fixed depth size and is independent to the data set, it has a constant amortized time complexity. So that is why half space trees is always faster than eForest ASD. We can see it on the left figure. But eForest ASD use less memory than half space trees, like you can see on the right figure. And for half space trees, window size has no impact on the model size. Only the trees increases the memory size. You can see it with the bar plot here. And this is consistent with the half space trees update policy, which consists on updating statistic in the tree node. So half space trees are in every node of every tree in the forest, half space trees cumulate a mass when updating the model. So the choice for the appropriate method depends on the context. And in the paper, we provide some guidelines to do the choice. To conclude, in this work, we present and we highlight the advantage and drawback of different approaches. We also implement we plan to implement the adaptive Windows concept in to improve concept drift detection in both methods. We also plan to extend circuit multi-flow with different existing methods for which we can propose some improvement for better performances. These are some references we use in our paper. Thank you for your attention. If you have any question.
Thank you, Moras. Very nice presentation, and you stopped in time. So I want to know if there are any questions or any remarks. Any questions? No? Just want to know, so you developed software, yes, that is available in the GitHub. This is the first version, or have you already developed some time ago?
The method was already proposed. The method E4S ICD was already proposed, but we implemented it. We implemented it on circuit multi-flow, and it is our implementation which is available on GitHub.
Okay, your implementation and the other method, the alpha something more. Sorry for I don't remember the name. This is the iForest, and there is another software. Yes.
Yes, Half-Space Trees.
Another implementation, Half-Space Trees.
Yes.
Oh, this is from the same. Okay, okay. Thank you. So this is developed in Python and is available for free.
Yes,
in the GitHub.
Yes.
Okay. Thank you. So if no more remarks, we can go to the next speaker.
Sorry.
Thank you, Mojas.
Sorry.
So now is. Sorry?
Can I ask a question to presenter?
Yes.
Yes.
Are these data your own data about trees or random? From random forest.
The data, you are talking about the data we use to our implementation, or the data are available on the public data. So we got it on the website. I don't remember.
Thank you. Thank you.
Yes, it's UCL machine learning.
Okay, we will have the paper available next soon. Then you can check some details. So the next speaker, please, Bruno. He will talk about towards integration of containers into scientific workflows, a preliminary experience with cached dependencies. Please share your application.
Okay. So, are you seeing my presentation?
Yes.
Okay, thanks for introducing me. My name is Bruno Alves. I am an undergraduate student at the University of Santa Maria. And I will present the work title Towards Integration of Containers in Scientific Workflows, a preliminary experience with cache dependence. So this paper is based on my graduation project, which was developed with the guide of Professor Andrea Charão. So scientists from various fields use software tools to process the data collected from experiments. However, in order to use software tools, scientists need to install and configure an entire environment. Is it another barrier to research? Yes, it is, and this is caused by the following reasons. Many scientists do not have specific computer skills. Environment configuration can be a challenging job even for experts. Reproducibility is compromised. Moving one workflow to another machine can result in a bigger problem. Scientists around the world have different resources. While the lucky ones have access to a supercomputer like Summit, other enthusiast students like me can have only a cluster of Raspberry Pis. So the initial barrier can generate disinterest and then slow down the advances on the area of research. Then, what we need to run workflows with more flexibility? We need containers. They represent a lightweight virtualization capable of isolating the application and its dependence. Despite its advantage, integrating containers in scientific workflows give rise to performance and design issues that must be carefully examined. Some authors have already investigated the integration of containers and scientific workflows. Zhang and Tyne explored Docker along with the workflow engine, called Makeflow, in a set of experiments comparing methods of connecting containers to the infrastructure. They take into account the cost of creating and deleting containers, considering a real-world bioinformatics workflow named BWA. So our work goes further in the track opened by these previous efforts. We focus on performance of each task and how different strategies can decrease execution time for another two real-world bioinformatics workflows, BLAST and HESIO. We also explored deeply Docker and two of its facilities, Docker Swarm and Docker Volumes. Docker Swarm is an orchestrator. It allows the user to manage multiple containers deployed across multiple platforms. So, a workflow describes how processes must be coordinated to achieve a common goal. The basic structure in a workflow is a process. It has an input data, the computation, and it generates an output. Makeflow has a simple way of describing a scientific workflow. You use a file with syntax similar to Unix makefiles. A task is described using the following parameters: input files, command to perform the task, and output files. Here we see an example describing two simple tasks. We classify dependence in two broad types: input and output dependence, the set of input and output data files that each task receives and generates, and also implicit dependence, scripts, binaries, configuration files. Those dependencies are known before the execution and they are static, do not change at any phase. Here we show the system components. We have host A and host B. Connect with the overlay network configured with Swarm. The manager node is located at host A, where there is also a local image repository, which is a container that acts as a local repository of all previously created images. Host B here contains only workers running inside of containers. So, the workflow execution is usually an iterative process, as scientists can add or remove tasks to the flow as the work evolves. So, a cache system can reduce data transfer over the network. The work queue cache system works in a way that the work queue manager, the green box here, stores a hash table which associates a worker identifier, the key, with the files the worker has in cache, the values. Each worker, when started, receives a unique identifier, here represented as node 1 and node 2. To circumvent the problem of container volatility, we set up a person Docker volume stored on the host native system. It was necessary to add a notification to the work queue communication protocol, the yellow box. This is sent by the worker nodes to inform the manager that they already have files in their cache. So, even if the container is turned off, the data stored on these volumes remain accessible. The advantage of a Docker volume is that multiple containers can access the same volume, sharing that data. For the experiments, we aim to evaluate the impact of the proposed cache system on HESIL and BLAST. Host A has 4 cores with 2 threads per core, while host B has 2 cores, also with 2 threads per core. We propose 2 strategies to test performance of the workflows. We tested 1 container per thread with 11 workers, where 4 workers are run on host B and 7 plus 1 manager on host A. We also tested 1 container per host, where we had 1 worker at A and 1 worker at B. For the results, on the left here, we can see that the longest execution time for BLAST was obtained with 11 works and the default work queue. Despite having more workers, this case performs slowly, because sending all the input files to all containers generates a bottleneck in which workers were delayed and the parallel execution was hampered. Although, on the other hand, the modified work queue led to the best execution times, because the files were already in the Docker volume of each host. On the right, HESIL workflow obtained the shorter times with only 2 workers. This happened because this workflow comprises tests where thread-level parallelism is better used than host-level parallelism. In general, these results suggest that the mapping strategy should be chosen carefully. For the conclusions, containers can provide flexibility to scientific workflows. We have proposed a cache system leveraging Docker volumes and work queue. Our experiments have shown that using the cache was beneficial for both workflows, and considering between container per host or container per thread is a decision that depends on each workflow and will impact its performance. For future work, we intend to develop an adaptive system where the mapping could be evaluated as new rounds of the workflow are executed. We also intend to expand our experiments to other real-world workflows and describe them with the Makeflow language. Thank you.
Thank you, Bruno. Still have time to one question. Anyone? You can raise your hand up. No? Okay, let's go to the next speaker. Thank you, Bruno.
Thank you.
Now, the next speaker, I'm asked, please upload your presentation. This is okay. The next presentation will be prevalence of cryptosporidiasis in northern Kazakhstan.
Экран можешь сесть? Ты презентацию опять. Вот он. Все.
Так. Thank you. Hello. Do you hear me?
Yes, we hear you, but we do not see. We see your face. We are not seeing your presentation. I don't know.
Sorry.
Are you sharing? Yeah. A button on the left bottom. You have like a screen. You can share your screen or application.
Слева нажать на экран надо и выбрать.
You cannot minimize your presentation, so just
Sorry.
Слева есть иконка экран в нижнем левом углу. Показать.
Do you see? Sorry.
Now we can see.
Okay, thank you very much. Sorry for some problems.
If you want to start to put, yes, full screen. Thank you. You can start.
Okay. Hello, I presented Siful in Kazakh Agro-Technical University, and here we presented some results of our investigation of cryptosporidiosis. This is emergent diseases what caused by protozoa species, and this is a widespread pathogens of many vertebrate animals and the humans. Parasites have a global distribution and cause epidemiological outbreaks of cryptosporidiosis among people with symptoms of diarrhea, abdominal pain, and other. For those living in endemic areas, immunocompromised people such as infant, malnourished subjects or patients with T-cell immunodeficiency conditions, for example, HTV infection, symptoms can be severe and even dangerous. And you see that in Milwaukee City in USA, there was an outbreak of these diseases where there was infected more than 400,000 people. Cattle may be main source of cryptosporidium of people, and the transmission of parasites from cows is common in outbreaks in human populations. Unfortunately, in Central Asia, there is only sporadic information about cases of human infection with cryptosporidiosis, although prevalence of cattle cryptosporidium in northern regions of Kazakhstan is relatively high. Therefore, studies of the epidemiology of the disease in the region in order to ensure the safety of human population are considered relevant. This research aimed to model the cryptosporidiosis distribution in calf population in the farms of northern Kazakhstan using the Bayesian inference method. Epidemiological data were collected in 2018-29 in 10 districts of the Akmola region, including 75 farms of different types. Feces were sampled from about 900 calves in 3 age groups. Some were examined microscopically for presence of cryptosporidiosis and staining with routine method and with special immune express methods of diagnostics. The observation followed binomial distribution, and the concept of starting with a beta prior and getting the beta posterior is used when a posterior is the same distribution family as the prior. The conjugate prior for binomial likelihood is the beta prior. The prior and the data contribute to the posterior distribution. Rather than work out the integral in denominator, we can use the kernel of beta distribution. Thus, this was our distribution, what we were used for computer uh, 80% of Akmola region districts. The study showed the problem with cryptosporidiosis in more than 20% of farms. Parasites were more widespread in large agricultural enterprises specializing in dairy production, comparing to small producers and private farmers. Results of computer simulations were follows. We see that the maximum likelihood was about 0.04, and the posterior was lying between 4 and 7%. for assessing the prevalence of cryptosporidia among sexes, we did other computer simulations, and we established that the MLE was in females about 4%, posterior was between 6 and 8%, and among males, the picture was similar, and the MLE was about 4%, and the posteriors was lay between was about 6%, and credible intervals for that was between 5 and 9%. So credible intervals for male and female animals were similar. The posterior distribution for females and males of 100,000 random samples were simulated, and the average empirical probabilities for females and males were about 6% in all sexes respectively. And after these simulations, we did the conclusion that sex of animals does not affect infections with cryptosporidiosis. In this cross-sectional epidemiological surveillance, we often have had small sample sizes of feces, which were dependent to seasonality of calving and limited possibilities to collect and investigate enough and equal samples in different types of livestock enterprises and householding farms. Therefore, we use this Bayesian inference, which has an ability to do sequential updates, using previous posterior as a prior to do another update makes straightforward sequential analysis in Bayesian statistics. It is appealing and practical for predicting the prevalence and the population dynamics of epidemically important diseases of people and animals. Results of computer simulations among ages of calves show that the biggest prevalence was in calves with age less than 1 month, and it is fitted to the literature data and shows that the calves under 1 month is the main source of cryptosporidia for people. We think that Bayesian inference technique allowed for predicting the prevalence of disease and planning measures to control cattle cryptosporidiosis in the conditions of different types of enterprise in the Akmola region. This work was made under the grant of Ministry of Education. Thank you for your attention. Please, questions.
Thank you. Any question or any remark?
Okay, may I ask?
Yes.
So, thank you for the presentation. As you can, as I see, you consider only portion of infection. Do you
Sorry?
Sorry, we can hear in good conditions. Can you put your
explain that?
Actually, my question is, as you can see, you consider only portion of infection.
Yeah,
and the question is, do you plan to consider the time of infection? How long has animal infected?
Thank you for your question. In the first step of our research, we analyzed only prevalence of the infection, and the next step of our research, we will research other characteristics of these diseases, epidemiological characteristics, and analyze all the risk factors of these diseases. And it will be presented in next our steps.
Okay, thank you.
Thank you.
Thank you. So just a remark. We have you send your paper to the general track, no problem at all. But we have a workshop on computational and applied statistics here in this conference. Maybe next time you can send submit your paper to that workshop. You can check the workshop because people that are attending the workshop are more statisticians and people that do kinds of studies like you did. Okay, so maybe more discussion is available in that workshop. So the paper is submitted here in ICCSA also, but you select the workshop. Okay. Just another remark. You are the name of the authors is in the program. There's only one name, one author. That is not you. It is.
No. Yeah. She is correspondent author of this.
So the paper.
I'm the first draft author.
Yes, it's okay, no problem in being you the presenter. But the paper, how many authors does the paper have?
Four authors. Four.
But
because
in
it's a group of research.
Okay, so my suggestion is to go to your submission site and then fill all the authors you have in the paper. Okay, because there's only one author, just the first one. You have to add all the authors there. Okay.
Okay.
Go there again and update the camera ready and with the last version you sent. Okay, but include all the authors that are in the paper.
Okay. Thank
Just
you.
to not having problems with the publication is my suggestion. Okay.
Thank you.
Thank you for your presentation. And next year I want you in the computational and applied statistics workshop. Okay. Just a suggestion again. So the last speaker is Thomas, I suppose. I'm not sure if it is Thomas or another name.
Yes, Thomas. Hello.
Thomas. Okay. So you will show some computational. You will talk about computational models of defect clustering for tethered bilayer membranes. Okay. Thank you. You can start. Please share.
I'll share my slides.
Yes. So maybe this is another. This is machine learning, no? Or clustering statistics?
Not really. Yeah, although the term is it sounds like it might be related to machine learning, but however, no, it's not. I'll present it, but I hope it will still be interesting. Okay,
yes, of course.
Seeing how to share the screen.
The button in the bottom left bottom of the screen.
Yes, but okay, just one moment. I actually have two two screens. I have an external monitor
You can
and my
share.
laptop, so I'm not sure how to select the exact one.
You can
Just one
share
moment,
your
maybe I'll
application.
disconnect.
Okay, share your application is in the middle.
Yeah, just one moment. Okay. Okay, can you see my slides?
Yes, yes, you can start. Thank you.
Okay, so hello everyone. My name is Tomas Raila. I'm a PhD student at Vilnius University, Lithuania, Institute of Computer Science, and I will present our work done together with our colleagues, biochemists from Life Sciences Center, Vilnius University. And the title of presentation is Computational Models of Defect Clustering for Tethered Bilayer Membranes. So I'll start with a brief introduction into the area, what's it all about. So tethered bilayer lipid membranes, or TBLMs for short, is a versatile experimental platform used by biochemists in laboratory conditions to study various forms of interactions between membranes and various proteins. And one type of such interactions is with pore-forming chemical compounds or toxins, which might damage the membrane and might cause some membrane defects to appear. As you can see in this AFM image here, those ring-like structures are the membrane defects. So two common experimental techniques used in the lab are to study such defected membranes are atomic force microscopy, or AFM for short, and electrochemical impedance spectroscopy. So the second one, there's also an example of impedance spectrum here below the AFM image. And the idea is that that second technique, although it cannot really provide any specific structural information about the membranes as it happens with microscopy techniques. It's much simpler, faster, and cheaper to use. And our recent research was actually concentrated about the to see how can these EIS measurements how can they be used to extract some structural information about the defected membranes without resorting to microscopy technique. So we have one paper published on this topic in which we used finite element analysis to model different cases of TBLM membranes with different defect distributions, regular or random defect distributions. And one important finding in the earlier work was that clustering of defects has actually important effects in obtaining EIS spectra, and we cannot rely just on randomly distributed defects completely independently from each other. We have to actually pay attention to the clustering effects. So this study was precisely about the clustered defect distributions of these membranes, and we started with such questions as how to actually generate synthetic defect distributions to be used for modeling purposes, in which that the clustering effect could be adjusted somehow, right? Another question was how to quantify that clustering effect in both synthetically generated defect distributions and experimental ones obtained by using AFM technique, and how to differentiate between completely random defect distributions and the clustered ones. So for these purposes, we chose our main tool to analyze these defect distributions was Voronoi diagrams. This is a well-known computational concept. And so basically, by computing Voronoi diagrams for a set of 2D points in the plane representing the defects on the membrane, we're analyzing the summary statistics of those Voronoi sector areas, for example, standard deviation, skewness, or others listed here. So for example, if you can see the slides, this is the example of a random defect distribution, and this is the histogram of Voronoi sector areas. So we developed two different defect clustering models, which would allow us to synthetically generate cluster defect distributions. So the first one is called attraction model, and it's based on the idea that defects attract each other if they are in close proximity, if the distance between them is below some predefined threshold. And if they do, they kind of lump together into a cluster. So this model takes 3 parameters in total: that attraction threshold, defect density, and defect size. And as we experimented with this model, it resulted in defect distributions which looked somewhat like this. It would basically produce a number of tightly packed defect clusters of kind of similar size, similar defect count in each cluster, and the clusters themselves are arranged in a 2D plane in somewhat semi-regular fashion, right? And another model which we investigated is called LCN model, and it was based on the different idea that defect clusters in the membrane should form somewhat more complex structures of varying size and shape. And to model that, we borrowed one specific algorithm from computer graphics. This is called lattice convolutional noise, and this algorithm is can be used to procedurally generate realistic cloud or smoke textures. So we use this algorithm to first generate probability fields and then sample using that probability field to sample the coordinates of defects on the modeling plane. And we also introduced 2 additional parameters for this algorithm: the cluster size S and the minimal probability of defect appearance P. So as you can see, this looks kind of visually different from the attraction model. It produces kind of shows that the model produces areas of different defect density and in the modeling area. So we experimented with both of these models by generating a number of different synthetic defect distributions by using various parameter values of these models. And one key observation here was that if we just use the simple summary statistics mentioned before, for example, standard deviation of Voronoi sector areas, we cannot unambiguously tell the parameters which could have been used in that case to generate that specific distribution. Right? It's not enough just to use these values. But another interesting observation here was that when we started with random defect distributions, which are generated just by sampling coordinates of each defect independently from a uniform probability distribution, and when we ran that experiment a number of times and just averaged results together, we found out that the standard deviation of these random defect distributions is there's a specific value for that specific constant equals to 0.54, and it's also visible in some of these figures here. Basically, by decreasing the clustering effect by adjusting the parameters of these clustering models, we actually can generate defect distributions very close to completely random ones. We also did some experiments with actual experimental AFM data obtained in the lab. However, in this case, we had a very limited amount of such data, just 3 AFM images. But these images were selected in such a way that, according to experts, some defect clusters were actually visible in those in those membranes. So we tried to apply this methodology of computing Voronoi diagrams for these experimental defect distributions and just computing those summary statistics, standard deviation, and the other ones. And we found out that standard deviation is actually a good indicator showing if that distribution is in fact clustered, right? If we can, for example, if you can see that in all three of these cases, standard deviation of these experimental distributions is significantly higher than that special constant value of random distributions, which is equal to 0.54. But this is not the case for some other metrics such as skewness or kurtosis. So just to summarize, we presented and tested two different defect clustering models. Although in our main publication, which is currently in the process of being published, we chose to use the LCN model. We considered it to be more versatile, as it is it's not dependent on some specific defect distribution parameters such as defect density or defect size. And however, at the moment, we can still only talk about preliminary results due to the limited amount of experimental EFM data we used. But these results show that it's actually possible to distinguish between random and clustered defect distributions by using our approach. We also established a specific constant of standard deviation of Voronoi sector areas equals to 0.54. Basically, we used it as a baseline value to differentiate, to say that either defect distribution is random or clustered. And in future work, we plan to implement an automated method for defect detection in FM images, because at the moment it's done manually and it's very time-consuming and inefficient. Although this computer vision or artificial intelligence task is not so trivial, as the defects in the images are often overlapping, clustered together, and there are also more difficulties there. And once we do that, we plan to do a more thorough statistical analysis with a broader data set of AFM data. We intend to further develop these clustering models and apply this methodology not just on AFM images, but also on experimental EIS data as well. Okay, so I think that concludes my presentation. Thank you.
Thank you very much for your nice presentation. We don't have much time, but for one question, please. Okay, I had some problems in the connection. Your experimental data is available, or?
You mean the results, or if the models are somewhere implemented and available online?
Yes.
Not yet, but it will be. As I mentioned, at the moment we're finalizing the publication of this topic, and we plan to publish the code used for these clustering models.
Okay. Thank you. Any more questions? No? Okay, thank you all. This session is closing now, and we have to jump to another room. Thank you, and see you next time. Okay, see you next year in Sardinia. Thank you. Bye-bye.
See you.
Thank you. Bye.
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 Excuse me, is the Professor Abdurrahman in the room?
Hi, to everyone. Sorry, did you ask any question before? I couldn't hear it very well.
Are you Professor Abdurrahman?
I will be presenting, but at 1:30. My name is Yelibet Racedo.
Because in my program, I have the chairperson, Professor Abdurrahman. I don't know if he's in the room, and 4 presentations from the same author, Carlos Andrés Corazos Morales.
Yes, good morning, sir. We are here ready to start on the quarter modeling, and the other one is the cavity paper.
Okay, who are you?
I'm Cesar Cárdenas.
Okay. We are waiting some minutes for the chairman. Can you hear me?
Yeah, yes, I can hear you.
Just a minute, we see if the chairman come in the room.
Okay.
Okay, I think we can start with the first presentation if you want. If the chairman come while we are in a session, let the chair to you. Hello, can you hear me?
Yes, I can hear you.
Okay, if you want to start with presentations, we are ready.
No, okay. But do you have a presentation, or we have to show it here?
You should share your screen with the presentation.
Oh, sorry, yes, I'm missing.
You have in the bottom on the left of your screen the icon share screen, and you can select your program window with a presentation.
Okay, let me give me a second, please.
Okay, so the first presentation is a hybrid model of the analysis of human gait, a nonlinear approach. Is that right?
The hybrid model for the analysis of a human gait. I would like to let you know that the author of the paper couldn't make it today, so we don't have a chance to do a presentation for that one. This is a Brazilian partner of our research team, but he couldn't make it today, so we have to, sorry about it. But I will be in charge of the other ones. The other one was about open font numerical simulation with different cavity shapes, and the other one is mathematical modeling and identification of a quad rotor. So I will be in charge of those ones. Just give me a second, I'm downloading our presentation.
Have you some problem with sharing?
Yes, this tool doesn't give me the chance. I'm trying to share my screen, but I haven't been able to do it. I don't know if.
Which browser are you using?
I'm using Firefox.
Okay. Firefox seems to have some problem with sharing on GC. Do you have a Chrome or any other?
Yes.
browser?
Yes, I have Chrome.
Let's try to use Chrome. Maybe we can fix it.
Okay.
You're trying with Chrome.
Yeah, I'm trying with it. Just give me a second, please.
We can see your screen, so be aware for your passwords. Maybe it's better if you stop your sharing until you have a presentation, because you are seeing your screen.
Okay. Okay.
Okay, while we are waiting.
You see it now?
No, but is Mr. Abduan in the room? No, again. Okay. Now we are seeing your browser. Try to stop the sharing and do it again. Selecting your PDF.
It's there now. Can you see it?
Yes.
There. So good morning. Sorry for the delay, but I have some technical problems right here, but I've already figured them out. My name is Cesar Cardenas. I am the author of this, part of the authors of this paper. We named it Open Phone Numerical Simulation with different lead-driven cavity shapes. Here we can see on the first slide the names of my name and the authors that were the two part of this paper. All of them belong to our research team and our research network down here in our country. So in our university and institution. So basically, what we did was to develop to take into account the continuity equation, the Reynolds numbers, and momentum of equation, which are the main actually equations considered for this problem. And of course, based on these equations, we actually performed some simulations by using the OpenFOAM software, which is a free software for computational fluid dynamics (CFD) simulations. Based of these simulations actually were based on the benchmark of the cavity tip flow problem. That is part of when you are actually studying by using this software. I'm talking about OpenFOAM. There are different benchmark cases that are considered as a tutorial or something like that to be able to become a little bit more to get some more skills by using this software. And the benchmark cases give you the chance to develop your skills with this software because it's not easy. This the kind of complicated software. But basically, we consider the math model. Of course, in the paper, you're going to find more detailed information on the equations of this problem. But these ones are basically the basic ones, the equations that are the basic equation considered for the problem. Now you see we have just differential equation. Of course, actually what is simple form to do this and solve the problem. So here we have just a Reynolds equation. Sorry, I'm gonna just clarify something like here. We use the Reynolds number. We change the different Reynolds numbers. We use different numbers of these to be able to try to find out what the behavior of the fluid, the flow through the cavity, right? And the continuity equation can have any chance. Of course, also discrete size and the momentum equation as well. So one of the more important issues here is that the Reynolds number was changed during the simulations, in order to figure out what happens there with the behavior of the fluid through the different cavity shapes. So here we have basically some of the steps that the equation and the correct equation of pressure are solved. So velocity, pressure are adjusted, and the pressure is solved. We're gonna check down there and later in the presentation some of the results of this the actual algorithm does for us. So the step 3, second rectifying pressure equation is solved. Actually, all the equations are solved. The pressure and space correction. Those are going step 5 and step 6. The other is the discretized transversal equations are resolved. So if we have a solution actually that is converged, yes or no, we have the software or the algorithm stops. If not, the return to the starting point. Here is very important clarify that if the geometry has any problem, because we actually the software gave us a chance to based on coordinates, just on coordinates on points on X, Y, and Z. That way we can get the geometry that we decide. In other cases, when the geometries are more complex, we have to use a CAD software or something like that to be able to import it to the software and then to have the chance to solve the problem there in the open form. Actually, this is the software or the solver that we use, the pressure implicit splitting operator, which is PISO. I will use some steps. And here we have some of the control volume that we use. Well, I'm not going to a lot of detail this, but this is some kind of finite volume method, that I use to solve the problem. Here we have some of the main simulation. Actually, you go over the paper, you're going to find a different cavity shape that we use to that. Yeah, just take some. I just talking in some of the result that we get, some of the residuals versus the iterations that were necessary, or that the software used to resolve the equations. And this is the first cavity issue here, cavity shape. I mean, here we are showing the vortex counter. We of course I took just a vorticity that is generated there. It's initiated in some point of the cavity, and then it's propagated around the cavity, right? Then we have here iterations and the way the velocities and pressure are solved. This is the first case of the shape cavity, the square cavity, and then the trapezoidal cavity. We have here just I took the pressure contours. Of course, there's also the vortices generated here, and we have the residuals versus the iteration. So we can see here how velocity and pressure, behave in this case. Of course, we also plotted the current number. I will show you another one of this on another slide. All the current number were, some of them were a little bit over 1, the others one below 1. So according to the tutorial, be a nice solution. Then we have the split shape. Here we have we can see the vorticity generated there, and then we have here the current number, as I mentioned before. Of course, I decided to take this. Also, we got, of course, the residuals and durations required for the solution of the problem of the equations. But basically, here you can see that the current number is below 0. So, which is a good solution for this to have current numbers below 0. Then we have pressure contours here for the arc shape cavity. And the residual, because it is a very important difference regarding to the compared to the other ones. I mean, this one we have solution 1x, 1e, the velocities, right, and the pressure here, and we have the behavior and the iterations required for this for the solution of this case. So some of the conclusion here. Well, we have the open form tutorial for the 2D. This is remember that I have just to clarify to make it clear that the cavity problem can be solved in the 2D or 3D option that we have here. 2D for cavity driven, establishing some parameters for simulation purposes of an compressible isothermal flow. It means that the algorithm gives us the solver gives us some parameters that are already established. We didn't change that. We just changed the geometries. We changed the Reynolds number. Right, basically those parameters, and for all different cavity configurations, the current numbers are obtained over 1. But almost, as we can see in one of those, we had some current numbers below 0, particularly the square and the trapezoidal cases are the ones that get values of about 1 to be solved. And of course, I didn't show those ones here; those are in paper, just to make the presentation a little bit more small. Yeah. It seems that no matter the velocity value, the vorticity is always generated in all the cavity shapes using a uniform mesh. We didn't worry much about. We have a finer mesh, generated just a fine mesh, and with finer grids over resolution, ones might even improve the vorticity prediction. But as I mentioned, what I mean is we didn't worry about the finer meshes. We just have the mesh. We didn't consider finer meshes, but it would be part of another study and to find out if there's actually a better solution for the vortices prediction. The Ecofont solver has appropriate performance for the solution of the complex cavity flows, and it seems that the convergence of the solution of accuracy could increase by employing some another solvers. Simple, there are other solvers that are more complex and resolve other complex with geometries that are maybe even more complex or difficult. So basically, that was about this. What we did about this. About this paper. So I don't know if there are who have. I don't know if we have any question or something like that. We have here some of the references that we use at some of them. There are different studies regarding this. Maybe we can. We are thinking about moving forward to work with other different geometries and problems with CFD, not specifically cavities, but also with some kind of repulsion engines or something like that, rockets and stuff like that. There are very actually simple geometries that can be used for simulation of this kind of problem. So we are thinking about move forward to a 3D problem or even other problems by using CFD, specifically with the solver. Or the software, I mean the OpenFOAM CFD. That's all for this one. I don't know if there are some questions regarding this.
Yeah, thank you. Any questions from the audience? If there is no questions, we can go on with the next presentation.
Okay. Just give me a second. I want to worry.
Remember to stop your sharing so we will read your ideas.
All right. So.
Thank you.
Is it stop now? I think. So can you confirm you are seeing the presentation?
No, we are seeing the GC page.
There? No, not yet. There.
Using Chrome, yes.
Is it already there?
Are you still using Chrome?
Yeah, I'm using Chrome.
Okay.
But you are seeing it?
No.
Not yet? No, so.
Are you sharing the single window application or your desktop? When you click on the share icon, you can choose if you want to share one single application. Okay, so you can open directly your PDF, or you can show all your screen.
Oh, okay.
Okay, try to open. Okay, perfect.
Now is there?
Yes.
Okay, sorry about that. Because the first time that we use this tool. Sorry. Okay. The other one is the other one presentation is about the other a paper which is named the mathematical model and identification of a quadrotor. This is basically I'm going to, we have here, we have, you can see the authors, and co-authors, and my name is the main author is me, Cesar Cardenas. We have all the co-authors that took part in this paper. And here we have all the affiliation of them. I'm going to start by checking some, I'm going to try to summarize a little bit this, because it's a math model for this kind of unmanned area vehicle. It's big, extensive, you know, it's kind of complex model, but we are gonna try to summarize it the best way. Try to do the best to summarize this and to that you guys can understand. But we'll try to do here. Basically, we use the same model, the math model, for another paper to do some kind of control stuff. Here we're going just as a validation of the flight math model or the flight dynamics model, where we use also some kind of a control simulation in the to validate the model. But basically here we have on this first page on the first slide, we have the forces and the reference frame that are required to be able to have a math model. To be able to have a math model of this kind of vehicle. Where we have some assumption. Remember that this is a 6 degree degree of freedom vehicle for control stuff. And normally we can use 6 because we have just 4 inputs, which are actually the motor speeds. But we're here with the F1, F2, and 3, and the FT is the total force. That we just issue. There is an equation for that. And here we have also the attitude, the attitude angles, which are rho, pitch, and yaw, that you can see here, phi, theta, and all those. And then we have the body reference frame that is right there here, that is based on on the body of the vehicle. And the other one is the reference frame that is in air reference frame that is going that way. So there are some assumptions here just to make the model more not so big, and to be able to simplify actually the model. We have to assume some things. For example, the first that the quadrotors and its propellers are taken as rigid bodies. So this is also rigid body. The body of its frame origin coincides with the vehicle center of mass right there. Right, so and the B frame and axis coincide with the inertial frame. So we have the body frame. We have to consider 2 of them, 2 reference frames, the body reference frame and the earth reference frame, and the thrust and drag of each motor is proportional to the square of the motor velocity. Later on, you're going to see that the equation there are some drag and thrust coefficients that are considered in the equations or in the model actually, to be able to do some kind of to apply the model for control purposes, for example. So this is some of the assumptions, that are going to help us. So that helped actually out to simplify the model. There are different 4 variables here that basically I can show here, that are the inertial position, north, east, the altitude of the aircraft, the body frame, velocity, the angle, pitch angle, yaw angle, and all those that are related here, and actually the velocities and the angular velocities and linear velocities, that of course they are defined right here. As you can see, this is basically the Newton's law, basically as mass acceleration force equals mass times acceleration that we are showing here. We have in the simplified model some kind of double differentiation, simple differentiation, and the quadrature of course assumes symmetric. So it means that all moments of inertia equals 0 here, and we have this as a matrix form, right? So all of this information is used, for example, when you are going to, for specifically the moments of inertia were considered here in this problem for simulation purposes in order to validate the model. So I'm trying just to summarize this a little bit here. Basically, as you can see here, the velocities, the angular acceleration, and all that are considered in the model in all the vector forms or matrix forms, right? Here we have the actually rotation, and remember that the first slide. There we in the first slide, the idea was to show how the rotation of the vehicle and all the axes X, Y, and Z. And here we have those matrices, that when you have a rotation in X, rotation in Y, you have phi, theta, and C, right? You have all the rotation matrices right here when they are, multiply, because there is some kind of math operation there. Based on that operation, we have or we get this cosine matrix. The cosine matrix is very important for simulation purposes, of course, because all these angles, all these have different values, and there if you have different values, you change the value, you can try to find or try to understand the flight dynamics of the model, how it behaves when you apply, when you change actually different angular values or angle values or additive angle values. So this is basically what this one shows here, a summary of the kinematics and dynamic summary of all the equations of the model. So it summarizes everything right here. Is summarized the cosine matrix. This matrix multiplied by these velocities, and where we have also the differentiation here. Some matrices that involves and some of the coefficients that we mentioned before at the beginning, drag coefficients, and even thrust coefficients. And here we have another assessment. Don't wait to simplify, just simplify the model here. Of course, you go over the paper, we're going to find always also the simulation of the mathematics or the math model of the propeller, motor dynamics, propellers, and all that. Right? I didn't include that just to, of course, because we have enough time to do that and to go in detail over those. But here we have been showing just the dynamics and kinematics of the quadrature, and of course that. Of course, you see in this matrix right here, we have moments of inertia and also the torque, the torque and moments of inertia. Basically, for simulation purposes, we could consider drag coefficients, thrust coefficient, moments of inertia, mass that we have here is the mass, right? And if, for example, we took if all these, so it looks, it's pretty much, a lot of variables, but there are some also assumption that, for example, if theta, although these angles are small, so this, for example, this expression right here is going to simplify to something like this. And this is what we did actually, based on the previous research studies on this topic. Always the model is simplified to some kind of U variables that I will show you later in this presentation. Here we have some of the dynamics of the equation model given, or is given by this expression, the model dynamics stuff. But as I mentioned before, this is more, there are more details on this model on the paper. So here we have just basically the Kirchhoff's law. And this is trying to show here Kirchhoff's law. Then motor torque, drag torque, load torque, and thrust. The expression that you can define it that way, and that in terms of those variables or those equations are in terms of drag coefficients, moments of inertia, moment of inertia of the motors, and some coefficients, some constants that are taken, are considered here. But this is pretty much the model, very basic model of the equation of the motor and propellers, right? So then we have here with all the information that we considered before. So we have a very simplified model right here, with which we consider just the attitude of the equator and the altitude. So for control purposes or simulation purposes, so as I mentioned before, with 6 degrees of freedom, to control this kind of vehicle is going to be really tricky, really difficult. So that's why we use a simplified model, and it's required a simplified model. So with the simplified model, you can see all the information of the variables that we have here in terms now of U2, U3, and U4, right? The paper gives you more details on how we get to this, and also the altitude, how it is simplified, but a more simplified equation here, expression for the altitude. So with all this information, now we need to take some variables, some values of the moments of inertia and mass, right? And with all this information, we use some kind of simulated model in order to validate this model, and how try to understand how the flight dynamics of the vehicle is when we change the moments of inertia, we change the mass and stuff like that. We use this based on this is the physical actually parameters of the AR drone, which is a commercial vehicle that you can buy out there, and based on those variables, on those values, we got this kind of result. I can say that this is very, very difficult to control. As a conclusion, even that conclusion, I can say that's very difficult to control one of these platforms. This platform has if you have moments of inertia that are very small, you're going to have really, really difficulties to be able to control this. The larger the moments of inertia, the larger the mass, the better the solution, the better the control stuff. So the better it is controlled. So we have 2 options here, because we try to use a PID control, which is shown here. PID, it's a classical technique, and PD control. With both, we could get some, we could stabilize the platform, but it was very difficult because, of course, we have to change actually the PID gains and the PD gains to be able to stabilize the platform. Right, so here we have to show you some of the results that we use based on the math model. The idea was to validate it through these performance simulations. So we have actually the result for all altitude angles, which is all roll, pitch, and yaw, and the altitude C in the same here, right? As a conclusion, I mentioned some of them already. Moments of inertia value may be higher. If they are higher value, actually the behavior and to be able to stabilize the platform is going to be easier. For example, there are more oscillations when the moments of inertia are small. When the mass values are not so small, better altitude stabilization is achieved. The drag and thrust coefficient, as well as motor speed, should be higher. The control simulation showed that also overshoot. That was just normal. And even when the mass of the quadrotor is very small, or with a small values of mass, to try to stabilize the quadrotor is very complicated. It's very difficult. So we have to use some bigger values of mass, for example, and to change the gains of the PD and PD model, control model. So there's important overshoots, but actually the stabilization is achieved. The attitude changes are very fast in time. This might be uncommon, but there are some kind of similarities with other research works. As at the beginning, we were having some kind of trouble trying to understand why all those changes were very, very, very fast. What I mean is that we found some graphs and plots that we couldn't understand at the beginning, and how the behavior of that, but as we changed, adjust PID gains, PD gains, some of the dynamic variables with higher values, for example, for mass and the moments of inertia, was better. So it's important not to see, for example, in this case, when you have, for example, we try to do something, we didn't include in the paper. While we also try to, but I mentioned this conclusion, or I talk about this conclusion because maybe we're thinking about moving forward to analyze not just this kind of platform with U inputs, just with V inputs. Also with V input, it means the input voltage inputs from all the motor propellers, right? So in that case, if you have a big voltage difference in the Roche dynamics low voltage inputs, it's important not to see a big voltage difference. But I mentioned this is, as I mentioned, this is going to be part of another study that we did. So we're going to try to move forward and to go in more detail in another future paper further. So otherwise, it would be not possible to get results similar to previous studies if we will use this. But this is an important issue. I wanted to bring this conclusion because there are just a few studies based on voltage inputs. Most of them are used based just on U inputs that we saw before. So there is some here, some of there were a lot of references and different studies from here based on the end of my master thesis work. But there are many papers and studies but the contribution that I want to remark that the contribution of a paper is that they are not, you can find a very complete math model. So here this is for me, this is a very important contribution to have a very complete math model in this case. So that involves motor propeller dynamics and the whole complete the detail on how to all the math detail, and how to complete and to have a complete model. I mean, so this is just one of the references that we use, and I don't know if there are some questions regarding this.
Thank you. Any questions from the audience? Okay. So we have 2 more papers. I don't know if the speakers are here. Mr. González Morales. No? Okay. Then I think we can stop this session. Thank you.
Sorry, I guess. Hi.
Yes.
The next presentation will be to invite me, Yelivet Racedo.
Sorry. Can you repeat?
Yeah, my understanding is that I have a presentation in this room.
Okay.
The work is titled Improving Fresh Fruit Bunches.
Okay, because sorry, I have the same author for all the papers. That's because I called for González Morales. But if you have a presentation, it's okay.
So can I start with the presentation?
Sorry, I can hear you well.
Can you hear me well now?
Yeah.
I wonder if I can start with the presentation.
No, I don't need to. Can you present? Do you have the presentation? Can you present this work?
Yes. Yes, I already have the presentation. I'm ready for doing.
Okay. You can ask the questions.
Yes, I'm gonna share my screen.
Okay.
Can you please confirm if you're watching it?
You can see. Okay. You can start. Thank you.
Okay. Yes. Well, my name is Yelivet Racedo, and I want to share with you the result of our work, which is titled Improving Fresh Fruit Bunches Unloading Process at Palm Oil Mills with Discrete Event Simulation. The outline of this presentation includes an introduction, a description of the supply logistic process of the palm oil mills. And I also present the simulation model and the case study that we use for solving the approach, or to present the approach, and finally, the concluding remarks. Well, palm oil is one of the main sources of oils and fats in the world, and Colombia is one of the producers of this oil in South America. This sector has shown a positive growth in recent years. In fact, in 2017, for example, we have a variation of 41% compared to 2016, and also the area used to cultivate this palm has also presented growth. Fede Palma, which is the Colombian National Federation of Palm Oil Cultivators, divides Colombian area in 4 geographic zones, and in all these zones, there have been a remarkable performance in production. And because of that, this is an important sector for the Colombian economy. Research have been done in order to improve the different processes of the supply chain. However, this agro-industry particularly face cost in the process of cultivation, harvesting, and production that can be higher or that are higher than those experienced for international competitors, just like Indonesia or Malaysia. And because of that, research effort have to be done in order to optimize the process. As a result, this project aims at developing a simulation model to evaluate and optimize the reception of the fruit at the mills in order to minimize the time of the design of the system, the time required to do the unloading process. And we evaluate some strategies that can be implemented without we evaluate some strategies that can be implemented at the tactical level without made a big investment, basically. Well, mills are usually located near to the plantations. So the idea is to try to process the fruit as soon as they are harvested. And harvesting may occur every day through year. However, the quantity of fruit tend to be higher during days close to mid at end of the month, which also makes more difficult the planning of the collecting process and the production process. As a result, we try to focus this research in the three first step of the figure number 1. And we try to modulate or simulate from the reception of the fruit to the unloading process of the different vehicles that arrive at the mills. So in order to try to explain a little bit the reception, waiting and unloading process, we present a flow chart. As can be seen, the operations or the process began with when the vehicles arrive at the mills. Once the vehicles arrive, the workers or the person responsible for letting the vehicles enter to the facility assign or give an ID in order to record information related with this vehicle, such as supplier name, the type of vehicle, the arrival time. And also it allows to record information just as the cargo that is transported by each vehicle that enters to the mill. So once the vehicle gets into a mill, it goes to the waiting area. And after that, the vehicles go to a waiting queue to be unloaded. At this point, an employee completes an application form with the arrival time. And also, if there is an available place to unload the vehicle, employee sends the vehicle to the platform and the unloading process begins. This process can be different depending on the type of vehicle that arrive. In this case, we consider 3 types of vehicles: automatic trucks, non-automatic trucks, wagons that are towed by tractors. And depending on the vehicle, we may need workers to manually remove the fruit using hooks. Once the unloading process ends, vehicles go to the waiting area again to be in order to calculate the net weight of the cargo, and the vehicle leaves the mill. In order to do a simulation process, we use the data. We have access to the system information of the company. We try to recover the information that is collected through this ID that I mentioned before. This information was used to estimate the statistical distribution for the inter-arrival time, and also to estimate the statistical distribution of the cargo that is transferred by each type of vehicle. Since the companies are usually interested in reducing the time that a vehicle remains into a mill, we use this as a performance indicator, and basically we use the average time in system, which is the time that the vehicle is inside the mill or into the mill, and also the maximum time in system, as I will present later. Well, we use the software CMU, and we take into account the standard and the flow library. We use that because this model is not completely discrete and discrete in simulation, because we try to combine some element of continuous and discrete modeling in order to increase the accuracy of the model that we try to use to evaluate some strategies. And for that, we also take into account some assumptions. One of them we present here. For example, we take into account that mills used to operate 24 hours. However, there is a time window for fruit reception. Also, that there are 3 types of vehicles. We also take into account the assumption that the extraction process at the mill is not interrupted. So the fruit consumption is known and constant during the day. And also that we have enough wagons to for storage fruit when the fruit is removed from the hoppers. And since there are enough wagons, there is not a constraint to take into account when we're modeling the process. Here, there is the structure of the model that we built in CMU. The vehicles arrivals are represented by 2 different sources. One source is for trucks, and that includes automatic and non-automatic. And also, we have another source for the small wagons. These entities contain kilograms of fruit. Next, they get into a self-named weight match, and later the vehicles are transferred to a station. They remain into the station until they can pass to the next stage, which is the unloading process. For this, we use a logic process. Basically, we try to establish that if there is an available place, they can move them. Otherwise, they have to wait until the unloading process are available. After that, we use an empty object to model the process that empties the content of the vehicle. This allows to model the filling of the hopper, and the vehicle is monitored through a tally statistic that allows me to collect the time between the arrival and the loading ending process. The tank, we use a tank object, which is named hopper, basically to represent how the hopper works. They receive the fruit until the fruit is removed from it. And we used to do that by using a regulator flow. This regulator flow allows me to model that every hour a specific amount of fruit is removed from the hopper and put it into wagons. These wagons are next getting to the extraction process, but we don't model that. We conduct an empirical case study using real data from a Colombian palm oil company. The mill has a processing capacity of 34 tons of fruit per hour, and also have 3 available places to unload the fruit. As I mentioned before, it operates 24 hours per day, with a time window specifically for receiving fruit from suppliers. We use information of 12 days of operation from the information system in order to quantify the parameters that is shown in this table. Basically, we take into account the inter-arrival times, the entity for arrivals and for trucks, but we also take into account the entities per arrival for wagons. Is a random variable that we use to model as as a triangular distribution. Using these parameters, we estimate the average times in system for the current process, but also the idea was not only to evaluate how the company is working, but also how the process can be improved with some changes in the way that they assign priority to unload the vehicles that are arriving into a mill. In this case, we propose 3 scenarios, taking into account that the objective of this work was to estimate the potential reduction in the time of the system that could be obtained with modification of the unloading procedure. The first scenario that we take into account consists of enabling another unloading process that was out in these images as I'm showing you right now. This scenario consists of enabling another unloading process for those vehicles that have been parked in the station for over 2 hours. That means if a vehicle arrives into the mill and the unloading process are busy, the vehicle has been waiting for 2 hours or more, then we need to have an additional unloading places to serve the vehicles in order that they can leave the mill. This policy was one of the company was taken into account, but they need to have the information of enough data to decide if it was convenient to do it. Also, we take into account another scenario in which the additional entry can be used not only by those vehicles that have been waiting for 2 hours, but also for automatic trucks, since the time required for the loading process for the vehicles is basically lower than that is required for doing the manually unloading process. And also, we take into account an scenario 3, in which the maximum waiting time in a station for all vehicles is 1 hour. All these, the model for the different scenarios was prepared for run for over 360 hours using 10 replications and a 90% of confidence level. And the results are shown in this table. The result that we get indicate that if the company decides to implement any strategies, the average time in system can be reduced at least by 20%, and also the maximum time in system can be reduced at least by 35%. Obviously, depending on the scenario of the strategy that they decide to implement, some changes have to be done. But the point here is that they don't need to invest a big amount of money. In fact, they just have to get, for example, an additional worker, 1 or 2 additional workers, but they don't have to build another or expand their infrastructure or make additional investment in order to improve or to extend the unloading capacity at the mills. Also, these results allows to identify that the decrease of the delays in the system allows to improve the supplier satisfaction, which is one of the main concerns for this type of companies, since there are a lot of competition in getting the fruit for the extraction process. These are the concluding remarks of the paper. Basically, we use a discrete model for getting these results. Since the similarity between the palm oil mills located in the Magdalena and in Colombia, the simulation can be applied to other companies to evaluate improvements alternative. This is all my work and the results that we have to present you. If there are any questions, I'll be happy to solve it.
Thank you for your presentation. Any questions from the audience? Okay, I think we finished the session then. Yeah. Thank you. I'm sorry for technical problems and chairperson missing. I hope you enjoy the session. Thank you.
Thanks to you.
Right, welcome.
Thank you.
Thank you.